Hello there, and welcome to Science for Sleep, where curiosity slows down, questions stretch out comfortably, and science is allowed to wander at an unhurried pace. Wherever you are right now, whether the room is dark or softly lit, whether this voice is keeping you company through headphones or drifting through the quiet air, you've arrived at a gentle place to rest your thoughts. Tonight's exploration is a large one, possibly the largest question we ever ask, but there's no need to brace yourself. We'll take it slowly, one idea at a time, letting the scale reveal itself without pressure. The question we're circling around is simple to ask, and surprisingly difficult to hold in the mind for very long. How big is the universe, really? Not in a vague, hand-waving way, not in the sense of very big, or almost impossible to imagine, but in a careful, step-by-step way that starts close to home and gradually eases outward. The kind of question that doesn't demand an answer all at once, but invites you to stretch your sense of distance just a little, then a little more, until familiar ideas start to loosen and drift. Before we go anywhere, though, it's worth pausing right here. Where are you listening from tonight? Is it late evening, early morning, or one of those quiet in-between hours where time feels slightly softer around the edges? Maybe you're winding down after a long day, or maybe you're letting this play in the background as sleep slowly catches up. Wherever you happen to be, this moment is your starting point, and that's exactly where a journey about size should begin. If you find this kind of slow curiosity soothing, or if it helps your mind settle instead of race, you're always welcome to like the video or subscribe. It helps this calm corner of science find others who might need something gentle to listen to. No pressure at all. For now, just settle in, let your breathing do what it wants to do, and allow your attention to follow along at its own pace. When people talk about the universe, they often jump straight to the dramatic parts. Endless space, billions of galaxies, distances so large they barely fit into language. But that approach can feel overwhelming, like trying to understand an entire ocean by staring at the horizon. Instead, it helps to start somewhere solid, somewhere familiar, somewhere with weight beneath your feet. Right now, you are on Earth. Not as an abstract concept or a dot on a diagram, but as a physical place. Beneath you is ground, floorboards, carpet, concrete, soil, rock. Beneath that, layers of crust and mantle and core slowly shifting over spans of time far longer than any human schedule. Earth feels large when you think about mountains, oceans and continents, yet small enough that you can cross it by plane in a matter of hours. It is big in daily life, manageable in global terms, and already tiny when compared to what comes next. One useful way to approach the size of the universe is to notice how easily our sense of scale adapts without us realizing it. A room feels spacious or cramped depending on its dimensions. A city can feel enormous until you leave it behind and see it from the air. Even Earth itself, which once seemed boundless to early explorers, now fits neatly into a single photograph taken from space. Our minds are good at resizing the world when given time and repetition. What they struggle with is sudden jumps. That's why instead of leaping outward immediately, it helps to linger on what Earth actually is in physical terms. The planet is about 12,700 kilometers across from one side to the other. That number sounds precise, but unless you work with distances every day, it doesn't mean much emotionally. A better sense comes from experience. Driving for hours without leaving a single country. Flying across oceans while watching daylight fade and return. Seeing weather systems stretch across entire regions. Earth is large enough to contain billions of lives, countless ecosystems, and deep histories layered on top of one another. At the same time, Earth is suspended in space, not anchored to anything. There's no up or down in the cosmic sense, no shelf or surface holding it in place. It moves, it spins, it travels along a path around the sun at a speed that would feel absurd if we weren't all moving together. Roughly 30 kilometers every second, without wind rushing past or engines roaring, just quiet motion through vacuum. Already the scale is shifting. The sun itself feels familiar because it rises and sets each day, but physically it is enormous compared to Earth. You could fit more than 1 million Earths inside it, packed together with room to spare. Its gravity governs the paths of planets, asteroids, comets, and dust across an area so large that even light takes hours to cross it. Yet the sun, despite its size, is only one star among many. That's where the question of size starts to widen in a way that's hard to keep hold of. Because stars aren't scattered evenly like streetlights. They form systems, neighbourhoods, and vast collections bound together by gravity. Our sun belongs to one of these collections, a galaxy called the Milky Way. Even the name suggests something continuous and flowing, but physically it is a structure with shape, mass, and edges that can be described. Before getting there, though, it helps to pause again. Notice how quickly the conversation moved from the room you're in to a planet travelling through space. That jump already stretches the imagination, and it's only the beginning. There's no need to rush forward. Understanding the size of the universe isn't about holding everything in mind at once. It's about letting your perspective gently expand, then rest, then expand again. One of the challenges with cosmic scale is that the units we use in daily life stop being useful. Kilometres work well for roads and borders. Even thousands of kilometres can be pictured with effort. But once distances stretch beyond planets, new tools become necessary. Astronomers often use light itself as a ruler, not because it's poetic or mysterious, but because it's practical. Light moves fast, very fast, about 300,000 kilometres every second. At that speed, light can circle Earth more than 7 times in a single second. That fact alone begins to rearrange expectations. When you see sunlight, you're seeing light that left the sun about 8 minutes ago. It crossed space, uninterrupted, and arrived just now. If the sun were to disappear, which it won't, the change wouldn't be noticeable immediately. For 8 minutes, everything would look the same. This delay between events and observation is a quiet but important part of understanding size. Space isn't just wide, it's deep in time. The farther away something is, the older the light we receive from it. Distance and history become linked, not philosophically, but physically. That idea can feel slippery at first, so it's fine to let it sit in the background. There's no test at the end. For now, it's enough to notice that even within our own cosmic neighbourhood, distances are large enough that light itself takes time to travel. It's also worth noting how carefully human language handles these ideas. We say things like out there and far away, but those phrases don't capture the quiet vastness involved. Space isn't crowded, it isn't busy. Most of it is empty in a very literal sense. The distances between stars are so large that if you scale the sun down to the size of a grain of sand, the nearest star would be kilometres away. Not centimetres, not metres, kilometres. That emptiness is part of the size. At this point, some people feel a sense of smallness creeping in. That's a natural reaction, but it isn't the only one available. Size doesn't automatically imply insignificance. A single cell is tiny compared to a human body, yet life depends on it completely. Scale changes context, not value. As this exploration continues, the universe will grow larger with every step outward. Planets will give way to stars, stars to galaxies, galaxies to structures so vast they challenge our ability to visualize them at all. But none of that erases the fact that the story always begins somewhere specific. It begins where you are now, listening, breathing, existing in a particular moment. There's a temptation to think of the universe as something separate from daily life, as if it starts somewhere above the clouds or beyond the atmosphere. In reality, there's no clear boundary. Earth doesn't sit inside the universe like an object in a container. It is part of it, fully embedded, moving along with everything else. Even the air around you is shaped by cosmic processes. The atoms in your body were formed in ancient stars long before Earth existed. That's not meant as a grand metaphor. It's a straightforward result of physics and chemistry. Elements heavier than hydrogen and helium require stars to form them. When those stars end their lives, they scatter material into space, which later becomes planets, oceans, and eventually living things. So when we ask about the size of the universe, we're not asking about a distant abstraction. We're asking about the scale of the environment that made all of this possible, including you, including this moment. As the conversation slowly moves outward from Earth, it will pass through familiar territory at first, the Moon, orbiting steadily at a distance that seems close in photographs but is vast in practical terms. The Sun, dominating the local region of space, the outer edges of the solar system, where sunlight grows faint and travel times stretch into years. Beyond that, the distances increase dramatically. Stars become points separated by gulfs of emptiness. The Milky Way reveals itself as a structure so large that even travelling at the speed of light, it would take 100,000 years to cross from one side to the other, and yet the Milky Way itself will eventually become just one among many. There's no need to hold all of that right now. The important thing is the pace. This is not a sprint through facts. It's a gradual widening of perspective, one that allows the mind to drift without losing its footing. As we continue, the familiar will slowly give way to the unfamiliar. Numbers will grow, distances will stretch, and the universe will begin to reveal itself not as a blur of enormity, but as a series of connected scales. From the surface of Earth, the universe doesn't announce its size all at once. It reveals itself quietly, often indirectly, through small, ordinary moments. You look up, maybe it's night and the sky's dark, or maybe it's daytime and washed in blue. Either way, that simple upward glance is the beginning of every attempt humans have ever made to understand how big everything really is. Standing on Earth gives us a very particular point of view. We're upright creatures, oriented toward the horizon, used to thinking in terms of forward and backward, left and right. Upward is different. Upward has no obvious limit. You can follow it with your eyes, but eventually your neck stops, your vision blurs, or the light fades. The direction continues even when your perception does not. That mismatch between what exists and what we can comfortably sense is where questions about scale begin. During the day, the sky feels close. Clouds drift by, planes cut across familiar routes, birds trace looping paths. Everything seems contained within a dome that arches overhead. It's easy to forget that this apparent ceiling is an illusion created by atmosphere and light scattering. The blue colour isn't a surface. It's a result of sunlight interacting with the air molecules. Above that blue, there's nothing solid waiting. Just thinner air, then none at all. At night, the illusion changes. The sky opens instead of closes. Darkness replaces blue and points of light appear. At first glance, they look evenly spaced, like decorations hung carefully in place. But even this is misleading. Those points are scattered across immense distances. Some are relatively nearby, in cosmic terms. Others are so far away that the light reaching your eyes began its journey before humans built cities or recorded history. Yet from where you stand, all of that complexity collapses into a single visual experience. A dark background, small lights, occasional motion as satellites pass or meteors streak briefly and vanish. The universe doesn't feel large in the way a mountain range feels large. It feels distant, layered, and oddly gentle. For most of human history, this view was the primary source of cosmic information. There were no telescopes, no photographs, no measurements in kilometers or light years. There was only observation, repetition, and pattern recognition. People noticed that certain lights moved against the background of stars. They noticed cycles, seasons, the slow shifting of constellations over generations. The sky became a clock, a calendar, and a map all at once. What's important for understanding scale is that even early observers recognized separation. The moon did not behave like the stars. It changed position quickly, showed phases, and appeared larger. The sun followed its own predictable path. The stars, by contrast, seemed fixed relative to one another, forming patterns that persisted year after year. That distinction led to one of the earliest realizations about cosmic structure. Some objects are closer, others are much farther away. Even without knowing the actual distances, people understood that the sky was not a flat surface, but a deep space filled with layers. Standing on Earth, gravity quietly holds everything together. You don't feel yourself being pulled toward the planet because the pull is constant and evenly distributed. But gravity is the reason standing is possible at all. It's also the reason Earth itself is roughly spherical, why the atmosphere clings instead of drifting away, and why looking up doesn't result in falling off into space. This matters because scale isn't just about distance, it's also about mass and influence. Earth's gravity dominates the immediate surroundings. Objects near the surface fall downward. The Moon stays bound in orbit. Even passing asteroids are subtly guided by Earth's presence as they move through nearby space. From this grounded position, the universe feels stable. The ground doesn't move, even though it's rotating at hundreds of meters per second. The stars appear fixed, even though Earth is travelling around the Sun at tremendous speed. Our reference frame is comfortable, local, and misleading. One of the hardest things about understanding cosmic size is letting go of that comfort. Without losing orientation entirely, Earth-centered perception is practical for daily life, but it hides motion and scale that only become obvious when you step back conceptually. For example, when you look up at the night sky, you might see the Milky Way as a faint band of light stretching across darkness. It looks like a cloud, maybe slightly uneven, brighter in some places than others. Without context, it could be mistaken for a feature of the atmosphere or a distant fog. In reality, that band is the combined light of billions of stars forming the disk of our galaxy, seen from within. You're inside the structure you're observing, looking along its dense plane. The fact that it appears as a thin streak rather than a uniform glow already hints at immense size. Structures that small don't surround you like that. Only something vast can. Still, the view from Earth compresses information. Depth disappears. Brightness replaces distance. A nearby dim star and a faraway bright one can look identical. The sky doesn't come with labels or scale bars. Everything arrives at your eyes flattened onto a two-dimensional dome. This flattening is why humans struggled for so long to understand the true arrangement of the cosmos. Without tools, distance is inferred indirectly. Motion, brightness changes, eclipses, and parallax all became clues. Slowly, piece by piece, the idea of a layered universe took shape. Parallax is one of the simplest and most intuitive of these clues. If you hold your thumb out in front of your face and switch which eye is open, your thumb appears to jump against the background. That apparent shift depends on distance. Close objects move more relative to distant ones. Astronomers use the same principle with Earth's orbit. As the planet moves from one side of the Sun to the other over 6 months, nearby stars appear to shift slightly against the more distant background. The amount of shift reveals distance. It's a delicate measurement, requiring precision instruments, but the underlying idea is straightforward. The fact that this shift is so small, even for the nearest stars, is itself a lesson in scale. It tells us that the distances involved are enormous compared to the size of Earth's orbit. Even the stars closest to us are far beyond intuitive reach. Yet from the ground, all of this is invisible. The stars don't appear to shift. The sky feels static. Night after night it offers the same patterns, reinforcing the illusion of closeness and permanence. Standing on Earth also means experiencing the universe filtered through atmosphere. Air scatters light, blurs fine details, and limits resolution. This is why stars twinkle and planets mostly do not. Twinkling isn't a property of stars themselves. It's the result of turbulence in the air bending light unpredictably as it travels downward. That shimmering quality adds to the sense that stars are small, delicate points. In reality, many of them are enormous spheres of plasma, larger than the Sun, radiating vast amounts of energy. The twinkle is not fragility, it's interference. When telescopes were first aimed upward, this interference became obvious. Magnification revealed that planets had disks, not points. Moons appeared around other worlds. The Milky Way resolved into countless individual stars. Each improvement in observational ability expanded the perceived size of the universe without moving the observer at all. This pattern repeats throughout the history of astronomy. The universe grows larger not because it physically expands before our eyes, but because our ability to perceive it improves. Every time a new layer is resolved, the boundary moves farther out. From Earth, the horizon also plays a role in shaping perception. During the day, the sky meets the ground at a clear line. At night, that line dissolves, but the sense of enclosure remains. You're inside something, looking outward. It takes effort to remember that there is no shell, no ceiling, no container holding everything in. Instead, Earth is embedded in space. The atmosphere thins gradually, fading rather than ending. Satellites orbit not because they are above gravity, but because they are constantly falling around the planet rather than straight down. Even the idea of up loses meaning once you leave the surface. This gradual transition complicates the sense of scale. There is no moment where Earth stops and space begins. No boundary you cross where the universe suddenly becomes vast. The change is continuous, subtle, and easy to underestimate. At night, when the moon is visible, it offers a more concrete reference point. You can see its surface features with the naked eye. You can watch it rise and set. You can notice its slow drift relative to the stars. It feels close in a way stars do not. And yet, the average distance to the moon is about 384,000 kilometers. If you could drive there at highway speed without stopping, it would take months. Light, moving unimaginably fast, still takes more than a second to cross that gap. That distance is large enough to fit every planet in the solar system between Earth and the Moon with room to spare. This fact often surprises people because images compress space dramatically. Diagrams are drawn for clarity, not scale. Standing on Earth, visual intuition constantly underestimates distance. The universe exploits this weakness effortlessly. Another subtle influence is the way human bodies relate to scale. We evolved to navigate environments measured in meters and kilometers. Our senses are tuned to that range. Beyond it, we rely on abstraction and tools. That reliance can feel detached, even unreal, unless carefully grounded. That's why starting from Earth matters. It's the only scale that feels fully real without effort. The weight of your body, the firmness of the ground, the pull of gravity, the resistance of air when you move. These sensations anchor understanding. As the universe grows larger in the mind, it's useful to keep that anchor. Not as a limit, but as a reference. Everything else is scaled relative to this point, whether consciously or not. When you look up tonight or imagine looking up, you're seeing the universe from the inside out. Light arrives at your eyes, carrying information across vast distances, filtered by atmosphere, interpreted by a brain evolved for survival, not cosmic measurement. That process is imperfect, but it's remarkable that it works at all. From this position, Earth-centered but curious, it becomes possible to take the next step outward, to move from standing on the planet to considering what surrounds it immediately, to look not just up but outward, toward the nearest structures that share this region of space. That shift doesn't require leaving the surface physically. It only requires adjusting perspective slightly, letting the idea of Earth as a solitary island give way to the understanding that it is part of a system, a neighborhood, one that extends well beyond what the eye can see, but still close enough to feel connected. With that in mind, the next natural question becomes simpler and more specific. How far does our immediate world extend before it blends into something larger? If you step outside on a clear night, especially somewhere away from bright city lights, the sky can feel surprisingly personal. Maybe you've seen it from a backyard, a balcony, a quiet road, or through a window that reflects just enough of the room behind you to remind you where you are. From those familiar places, the universe doesn't announce itself as something vast and overwhelming. It feels contained within what you can see, framed by trees, rooftops, fences, or hills. The world feels like it ends somewhere above your head, even if you know intellectually that it does not. That feeling is powerful because it's shaped by experience rather than measurement. For most people, the sky's encountered in pieces. A few stars here, a brighter planet there, the moon rising slowly from behind a building. The idea that this view connects seamlessly to something unimaginably large takes time to settle in. It's not obvious. It has to be learned gently. From the ground, Earth feels like the entire world, not in a philosophical sense, but in a practical one. You walk across it, you live on it, you look out and see land meeting sky, water meeting shore. Even when you know Earth is a planet in space, that knowledge doesn't always translate into a felt sense of scale. It stays abstract unless you slow down and build outward step by step. The first step beyond Earth is not the stars. It's the space immediately surrounding the planet, the region that still feels connected, still influenced strongly by Earth's presence. This is where the idea of the edge of our world begins to make sense, not as a sharp boundary, but as a gradual transition. Earth is wrapped in an atmosphere, a thin layer of gas that feels substantial when you breathe but is vanishingly small compared to the size of the planet itself. If Earth were the size of a basketball, the atmosphere would be thinner than a layer of paint. Yet this thin layer shapes almost everything about daily life. It regulates temperature, shields against harmful radiation, and makes sound, weather, and clouds possible. Looking up from a backyard, the atmosphere is what gives the sky its colour, its softness, its changing moods. It's also what limits how far you can see. Even on the clearest night, air scatters light and blurs distant objects. Without it, the sky would be black even during the day, and stars would be visible at all times. As you go higher, the atmosphere thins. Commercial airplanes cruise at altitudes where the sky darkens and the curvature of Earth becomes faintly visible. Above that, weather balloons reach heights where air pressure is so low that unprotected humans could not survive. Still, this is not space yet in a strict sense. There is no precise altitude where atmosphere ends and space begins. For convenience, humans have defined a line known as the Kármán line, about 100 kilometers above sea level. Above this height, aerodynamic flight becomes impractical, and orbital mechanics take over. It's a useful definition, but it's arbitrary. Air does not suddenly vanish at that altitude. It simply becomes thinner and thinner, fading rather than stopping. Satellites orbit Earth within this extended envelope. Some skim the upper atmosphere, gradually losing altitude as they encounter drag. Others orbit much farther out, well beyond what feels intuitively close. The International Space Station, for example, orbits at roughly 400 kilometers above the surface. That sounds high, but relative to Earth's size, it's barely above the skin. From the ground, it's easy to imagine satellites as distant points far removed from everyday life. In reality, they are closer than many long-distance flights travel horizontally. They circle the planet every 90 minutes or so, moving fast enough to stay in continuous free fall around Earth rather than crashing down. This region around Earth, dominated by its gravity, is known as near-Earth space. It extends far beyond the atmosphere and includes not only satellites, but also debris, spent rocket stages, and natural objects passing through. Earth's gravitational influence does not stop at neat boundary. It weakens gradually, overlapping with the influence of the Moon and the Sun. The Moon is often thought of as the next major marker beyond Earth, and for good reason. It's the most prominent object in the sky besides the Sun. It has texture, shadows, and phases that change predictably. It feels like a companion rather than a distant point. Yet the space between Earth and the Moon is vast enough to challenge intuition. If you were to draw Earth and the Moon to scale on a page, the Moon would be tiny, and the distance between them would stretch across most of the paper. This empty space is not filled with anything substantial. No clouds, no haze, just vacuum, crossed occasionally by radiation and particles. That emptiness matters for understanding size. Our minds tend to compress space when there's nothing visible to mark distance. We imagine Earth and the Moon as neighbours because they appear close in the sky. But closeness in appearance does not equal closeness in space. The Moon's orbit defines a significant extension of Earth's immediate environment. Earth and the Moon form a gravitational pair, orbiting a shared centre of mass. Tides on Earth are shaped by the Moon's pull, subtly raising and lowering oceans twice a day. This interaction gives the Moon an outsized influence relative to its size. Beyond the Moon's orbit, Earth's dominance fades further. The Sun's gravity becomes increasingly important, shaping the paths of objects moving through this region. Still, Earth retains a kind of invisible reach. It has a magnetic field that stretches far into space, forming a structure known as the magnetosphere. The magnetosphere is not something you can see from a backyard, but it is part of Earth's true size in space. It's created by the planet's molten core, which generates a magnetic field that deflects charged particles from the Sun. This magnetic bubble protects the atmosphere from being stripped away by solar wind. On the side facing the Sun, the magnetosphere is compressed. On the night side, it stretches out into a long tail that extends hundreds of thousands of kilometers into space, well beyond the Moon's orbit. In this sense, Earth's influence reaches far farther than its physical body. Auroras are one visible effect of this interaction. When charged particles funnel along magnetic field lines and collide with atmospheric gases near the poles, the sky glows. From the ground, it looks like light dancing across darkness. From space, it's a sign of Earth actively interacting with its cosmic environment. So where, then, is the edge of our world? If world means solid ground, the edge is obvious. But if it means the region shaped primarily by Earth's presence, the answer becomes more complicated. Earth's gravitational influence extends outward indefinitely, weakening with distance but never disappearing entirely. Its magnetic field stretches and flexes. Its orbit around the Sun carves a path through space shared with dust, asteroids, and particles. From a backyard perspective, none of this is apparent. The sky feels like a backdrop rather than a dynamic environment. But once you begin to think in terms of influence rather than appearance, Earth's world grows larger. Another way to think about the edge of our world is through escape velocity. This is the speed an object must reach to break free from Earth's gravitational pull entirely. For Earth, that speed is about 11.2 kilometers per second. Anything slower, and gravity will eventually pull it back. Anything faster, and it can leave Earth behind. Rockets must reach this speed, or something close to it, to travel beyond Earth's immediate hold. Even then, they don't simply leave instantly. They climb, orbit, adjust, and gradually transition from Earth-centered motion to Sun-centered motion. This transition zone is not marked by a sign or a line. It's a region where gravity shifts from one dominant source to another. Spacecraft navigating it must account for overlapping forces, carefully adjusting their paths. The idea of Earth having an edge becomes less about borders and more about gradients. Influence fades, control loosens, motion becomes shared. Beyond Earth's immediate neighbourhood lies the broader solar environment. But before stepping fully into that, it's useful to sit with the realization that even this local region is far larger than everyday experience suggests. From ground to orbit, from atmosphere to magnetosphere, from backyard sky to lunar distance, the scale has already expanded dramatically. And yet, in cosmic terms, all of this is still very small. Earth's orbit around the Sun defines another meaningful boundary. The planet travels along a nearly circular path about 150 million kilometers from the Sun. This distance, called an astronomical unit, is used as a basic measuring stick for the solar system. From Earth, this distance is invisible. The Sun looks the same size throughout the year because the orbit is so large relative to Earth size. Still, this orbit marks a shift. Within it, Earth is one of several planets bound tightly to the Sun's gravity. Beyond it, the solar system continues outward through regions that grow colder, darker, and less familiar. But even before reaching the outer planets, the perspective changes. Earth is no longer central. It becomes one moving body among many, tracing a path through space that repeats year after year. Seen this way, the edge of our world is not a wall but a widening context. Earth gives way to near-Earth space. Near-Earth space blends into the Earth-Moon system. That system sits within the Sun's gravitational domain. Each layer adds distance, complexity, and scale without erasing the previous one. From the backyard, the sky still looks the same. Stars still shine, the moon still rises, but understanding what lies between here and there transforms the view. The darkness is no longer empty. It's structured, shaped by forces and motion. As this sense of scale settles in, it becomes easier to imagine moving farther out, not physically but conceptually. When people talk about the distance to the moon, they often reach for numbers first. 384,000 kilometers, 238,000 miles. Accurate, precise, and almost completely unhelpful to intuition. Those figures are correct, but they don't land anywhere in the body. They don't connect to lived experience. They float in the mind briefly and then slip away, leaving behind only a vague sense of far but not that far. So instead of starting with numbers, it helps to start with something familiar, something rhythmic, something internal, your heartbeat, for example. Right now, without doing anything at all, your heart is beating steadily. Maybe 60 times a minute, maybe a bit faster or slower depending on how relaxed you are. Each beat is a small mechanical event driven by electrical signals and muscle contractions. It's ordinary, constant, and easy to ignore. Yet if you counted heartbeats the entire time it takes light to travel from the moon to Earth, you would count just over 1 heartbeat. That's not a metaphor. Light takes about 1.3 seconds to cross the space between Earth and the moon. In the time it takes your heart to beat once, a signal travelling at the fastest speed anything can move has already completed that journey. That single fact begins to shift perspective. Because light is fast in a way that defies everyday comparison. It doesn't slow down when it enters space. It doesn't tire. It doesn't drift. It moves at the same speed whether it's passing through empty vacuum or glancing past planets and stars. When we use light as a measuring tool, we're not choosing poetry, we're choosing the most reliable ruler available. From Earth, the moon looks close. It fits neatly into the sky. You can cover it with a fingertip held at arm's length. You can watch it move night to night, changing shape and position. It feels reachable in a way that stars do not. Yet that reachability is deceptive. Imagine lining up cars bumper to bumper from Earth toward the moon. Even if each car were only 5 meters long, you would need more than 70 million of them to bridge the gap. Now imagine walking that distance instead. At a steady pace, without stopping, it would take years. Not days, not weeks, years. The space between Earth and the moon is not empty in the way a room is empty. It is empty in a deeper sense. There's almost nothing there. No air, no sound, no landmarks, just distance. This emptiness is part of what makes the moon's distance difficult to grasp. On Earth, distance is usually filled with things: roads, terrain, buildings, weather. Even oceans have texture, movement, and variation. Space does not. Between Earth and the moon, there is no gradual transition to help the mind scale up. You leave Earth's immediate surroundings, and then there is simply more and more of the same nothing. From a backyard perspective, that nothing collapses. The moon rises just beyond treetops or rooftops. It looks as if it's hovering not far beyond the clouds. But clouds are rarely more than a few kilometers above the surface. The moon is hundreds of thousands of kilometers away. This compression of distance is a feature of vision, not a failure of intelligence. Our eyes evolved to judge distances on Earth, where perspective cues are plentiful. In space, those cues vanish. Brightness replaces proximity. Size on the retina replaces actual size. The moon appears large because it is large relative to its distance. It's about 1/4 the diameter of Earth, which is unusually big for a moon compared to its planet. That size, combined with its relative closeness, makes it visually prominent. It dominates the night sky in a way no other object does. Yet even with that prominence, it exists in isolation. To understand the moon's distance, it helps to imagine removing Earth from the picture entirely. Picture a vast black space with only two objects in it. One is Earth, one is the moon, no stars, no sun, just those two bodies suspended in darkness. From that perspective, the separation becomes stark. Earth would be a glowing sphere, blue and white, and far away from it would be a smaller grey sphere slowly orbiting. Between them, nothing at all. That distance is large enough that astronauts travelling to the moon did not simply move in a straight line. Their paths had to be carefully calculated, curved, and timed to intersect the moon's orbit precisely. A small error in direction early on would grow into a massive miss over that span of space. During the Apollo missions, it took about 3 days to travel from Earth to the moon. 3 days of coasting through space, gradually leaving Earth behind, watching it shrink from a full world into a pale disk, then into a bright dot. From the surface of Earth, the moon's distance feels manageable because 3 days doesn't sound long, but those 3 days were spent moving at tens of thousands of kilometers per hour. At any speed resembling everyday travel, the time stretches beyond human patience. Light, by contrast, makes the journey in a blink. This contrast between physical travel and light travel is one of the clearest ways to understand cosmic scale. When light itself takes time, distance has meaning beyond imagination. The moon is close enough that this delay is short. 1.3 seconds is barely noticeable. When astronauts on the moon spoke to mission control on Earth, there was a small pause, a brief gap between question and response. It was subtle, but real. That pause was distance made audible. If you clap your hands and hear an echo from a distant wall, you're experiencing the same principle. Sound takes time to travel. The farther the wall, the longer the delay. Light works the same way, just much faster. The moon's delay is small enough that it feels almost immediate. But it is the first place where the universe reminds us that even at its fastest, communication is not instant. The moon's orbit adds another layer to this understanding. It does not circle Earth at a fixed distance. Its orbit is slightly elliptical, meaning sometimes it is closer, sometimes farther away. The difference can be tens of thousands of kilometers. This is why the moon sometimes appears slightly larger in the sky, an event often called a supermoon. That variation is subtle to the eye but significant in space. It means the Earth-Moon distance is not a single number, but a range. Even our nearest neighbour does not sit still. The moon also moves away from Earth very slowly over time, at a rate of a few centimetres per year. This recession is driven by tidal interactions between Earth and the moon. Over millions of years it adds up. In the distant past, the moon was significantly closer. Tides were stronger. Days were shorter. So even the distance we're talking about now is not fixed. It's part of a long, gradual evolution. When you think about the moon from Earth, it's tempting to treat it as a destination rather than a measurement. A place people have been. A surface with footprints. A goal that was reached and then left behind. But in terms of scale, the moon is more than a destination. It's the first clear marker of how large space actually is. It's the first place where Earth-centered intuition fails completely. Everything before the moon feels like an extension of Earth. The atmosphere, orbit, even the magnetosphere. But the moon sits apart. It is connected by gravity, yes, but it is not part of Earth. It is its own world, separated by distance that resists compression. That separation shows up in practical ways. No bridge could ever span that gap. No signal travels instantly. No rescue could arrive quickly if something went wrong. The moon is close enough to visit, but far enough to be truly elsewhere. From a backyard, it doesn't look that way. It looks gentle, familiar, almost comforting. But that comfort is visual, not spatial. If you were to place Earth and the moon on a scale model that fits on a football field, Earth would be about the size of a basketball. The moon would be about the size of a tennis ball, and the distance between them would stretch across most of the field. Standing next to Earth, you would not see the moon unless you looked far away. Most illustrations don't show this because it feels counterintuitive. They shrink the distance to keep everything visible at once. But that visual convenience hides the truth. The truth is that space begins asserting itself forcefully at lunar distance. Beyond the moon, there is no sense in which Earth dominates the scene visually. Earth becomes just another object. A bright one, yes, but not central. This is why photographs taken from the moon are so striking. Earth appears small enough to hold in your gaze. Entire oceans, continents, weather systems, all contained in a single view. That image reverses perspective completely. From Earth, the moon is a feature of the sky. From the moon, Earth is a feature of space. That reversal is essential for understanding scale. It shows that what feels large or central depends entirely on where you stand. The moon also marks the point where human presence thins dramatically. Beyond it, no one has travelled. Everything farther out has been visited only by machines. That boundary is not arbitrary. It reflects the increasing cost, complexity, and time required to cross larger distances. If the moon were twice as far away, lunar missions would have been far more difficult. If it were 10 times farther, they might not have happened at all. Distance is not just a number. It shapes what is possible, and yet in cosmic terms the moon is still extremely close. This is where perspective shifts again. The moon feels distant compared to Earth-bound experience, but compared to the distances between planets, it is nearby. Compared to the distances between stars, it is almost touching. The light delay of 1.3 seconds is the smallest delay we will encounter when measuring space in this way. It is the first step, the smallest unit in a ladder that grows rapidly. The moon teaches us how to think in light time without overwhelming us. It introduces the idea gently, one heartbeat, one pause in conversation, one blink of delay. As attention moves outward from the moon, those pauses grow longer. Light minutes replace light seconds, then light hours, eventually light years. But it's important not to rush there. For now, the moon is enough. It is far enough to break Earth-centered intuition, close enough to remain relatable, familiar enough to feel real, isolated enough to demonstrate the emptiness of space. From Earth, the moon looks like part of the sky. In reality, it is a separate world suspended in vast nothingness, connected by gravity and light, but separated by distance that cannot be ignored. As that understanding settles in, the mind becomes more comfortable with the idea that space is not just something above us. It is something between things, and that between can be enormous even when the objects themselves seem close. Moving outward beyond the moon, something subtle but important happens to the way distance behaves. Up to this point, everything has still felt anchored to Earth. Even when the moon stood apart as its own world, Earth remained the reference. Distances were measured from here, delays were counted relative to conversations on the ground, and perspective kept snapping back to familiar ground. Once you begin crossing the solar system, that anchoring loosens. The solar system is not a line you travel along, nor is it a neatly stacked set of rings waiting to be crossed. It is a wide, flattened region of space shaped by gravity, motion, and time. The planets do not sit in tidy rows. They move, each on its own path, each following a rhythm that has been repeating for billions of years. To cross this system is not to move straight outward. but to pass through overlapping orbits, each one marking a new scale of distance. From Earth, the sun feels close. It fills the sky with light and warmth. It shapes daily life so thoroughly that it barely feels like an object at all. Sunrise and sunset feel more like changes in state than changes in position. Yet physically, Earth is already far from the Sun. The average distance between Earth and the Sun is about 1 astronomical unit, roughly 150 million kilometers. Light takes a little over 8 minutes to cross that distance. That means every sunrise you've ever seen began its journey while you were doing something else entirely. Making tea, brushing your teeth, turning over in bed. 8 minutes is short enough to feel immediate but long enough to matter. It is long enough that if the sun were to suddenly change, which again it will not, Earth would continue receiving the old information for several minutes. The solar system is already operating on delayed awareness. This distance defines Earth's orbit, a nearly circular path that takes 1 year to complete. That year is not just a calendar unit, it is a measure of space. Earth travels the circumference of that orbit at roughly 30 kilometers per second, covering nearly 1 billion kilometers every year without ever feeling the motion. From the backyard, nothing about this movement is obvious. The sun appears to trace a daily arc across the sky, but that motion is due to Earth's rotation, not its orbit. The deeper motion is hidden, detectable only through careful observation over time. As you imagine moving outward from Earth's orbit, the next planet encountered is Mars. At its closest, Mars can come within about 56 million kilometers of Earth. At its farthest, it can be over 400 million kilometers away. That wide range exists because both planets are moving, each on its own track around the Sun. This variability is an important feature of the solar system. Distances are not fixed. They stretch and compress depending on where planets are in their orbits. Space here is dynamic, not static. Light takes between 3 and 22 minutes to travel between Earth and Mars depending on alignment. That means communication with robotic explorers on Mars is never immediate. Commands are sent, then there is waiting. Responses arrive later, carrying information from the past. As distance grows, waiting becomes normal. Beyond Mars lies a wide gap before the next major planet appears. This is not accidental. The solar system is not evenly packed. Most of its volume is empty space, with planets occupying small regions separated by vast distances. Jupiter dominates the outer portion of the system. It is massive enough to influence everything around it. Its gravity shapes the asteroid belt, captures moons by the dozens, and subtly alters the paths of comets passing through. Jupiter is more than a planet. It is a system within a system. The average distance from the Sun to Jupiter is about 5 astronomical units. Light takes roughly 43 minutes to make that journey. From Earth, that means sunlight reaching Jupiter left the Sun nearly an hour earlier. Signals travelling from Jupiter to Earth carry information that is almost an hour old by the time it arrives. At this scale, the solar system begins to feel stretched. Orbits are no longer things that could be crossed quickly, even at extreme speeds. Travel times lengthen. Communication delays become noticeable. The sense of immediacy that defined Earth's neighbourhood fades. Saturn lies farther still, at about 9.5 astronomical units from the Sun. Light takes over an hour to reach it. Uranus and Neptune extend the system outward even more, with light travel times measured in hours rather than minutes. By the time you reach Neptune, the outermost classical planet, sunlight takes about 4 hours to arrive from the Sun. That means Neptune exists in a kind of twilight compared to Earth. The Sun there is not a blazing disk but a bright star, still dominant but distant. The distances between these outer planets are enormous. Neptune is not just a little farther than Uranus. It is separated by billions of kilometers. The scale grows quietly but relentlessly. Yet even here, the solar system does not end. Beyond Neptune lies the Kuiper Belt, a vast region populated by icy bodies, remnants from the early formation of the solar system. Pluto resides here, along with countless smaller objects. These bodies orbit the Sun at distances so great that a single orbit can take centuries. Pluto's average distance from the Sun is about 39 astronomical units. Light takes more than 5 hours to reach it. A signal sent from Earth takes the better part of a day to arrive, and a full day for a response to return. When Pluto was visited by the New Horizons spacecraft, it took over 9 years to reach its destination. 9 years of continuous travel through space, passing planet after planet, crossing orbit after orbit, steadily leaving the inner system behind. That journey did not feel fast, even though the spacecraft was moving faster than any previous object launched from Earth at the time. The distances simply demanded patience. Beyond the Kuiper Belt lies the scattered disk, and farther still, the hypothesized Oort cloud. This region is thought to extend tens of thousands of astronomical units from the Sun. If it exists as predicted, it forms a vast spherical shell of icy objects surrounding the solar system. At those distances, light takes months to travel. Gravity still binds these objects loosely to the Sun, but the connection is weak. Passing stars can disturb them. Galactic tides can alter their paths. Here, the solar system blends gradually into interstellar space. There is no sharp edge, no wall marking where the Sun's influence stops and the galaxy's influence begins. Instead, there is overlap, transition, and gradual release. Throughout this outward crossing, one thing becomes clear. The solar system is not small, it is not compact. It is a sprawling structure where planets are separated by distances that dwarf the space between Earth and the Moon. Yet from Earth, all of this is compressed into a small patch of sky. Planets appear as bright points wandering slowly among the stars. Their true separation is hidden by distance and perspective. Understanding the size of the solar system requires letting go of the idea that space is filled evenly. Instead, it is mostly empty, with islands of matter bound by gravity and motion. Orbits define regions not by walls, but by patterns of movement. Crossing the solar system one orbit at a time means recognizing that each orbit is a milestone. Earth's orbit marks the boundary of familiar warmth and light. Mars introduces variability and challenge. Jupiter reshapes the architecture entirely. Saturn, Uranus and Neptune stretch the system outward into darkness. Each step outward adds not just distance but time. Travel time, communication time, adjustment time. Light becomes the most reliable guide. Minutes become hours, hours become days. Distance turns into delay. And still, even at the farthest reaches of the Sun's influence, the solar system remains only a small pocket within something much larger. The Sun itself is one star among hundreds of billions in the Milky Way. Its domain, vast as it feels from within, occupies a tiny region of the galaxy. But before stepping into that broader context, it's important to sit with what has already expanded. From a backyard sky to lunar distance, from Earth's orbit to the outermost planets, scale has grown quietly but dramatically. The solar system teaches an essential lesson. Size does not announce itself with noise. It reveals itself through patience, through repeated comparison, through the realization that what once felt far was only the beginning. As the Sun's influence slowly fades with distance, the idea of leaving it behind feels strange at first. The Sun has been the anchor for everything so far. Its gravity organized the solar system. Its light defined warmth, day, and habitability. Its presence made space feel structured rather than endless. Even when attention drifted outward to the farthest icy remnants of the system, the Sun was still there, faint but central, holding everything together. Letting go of that anchor requires a shift in how scale is understood. The Sun does not sit in isolation. It never has. It moves through the galaxy along with countless other stars, each following its own path, each surrounded by its own gravitational domain. The solar system is not a fixed structure embedded in space like a model on a shelf. It is in motion, carried along through a much larger environment. To leave the Sun behind is not to cross a sharp border. It is to pass through a region where the sun's pull weakens until it becomes just one influence among many. Gravity does not switch off. It thins, it overlaps, it competes. At great distances, objects once bound to the sun begin to feel the pull of other stars and the overall gravitational field of the Milky Way. This transition does not happen at a single point. It unfolds gradually over tens of thousands of astronomical units. By the time the sun's hold becomes negligible, the scale has already expanded beyond anything familiar. From Earth, stars look like points fixed in the sky. They appear evenly spaced, distant and unreachable. That visual uniformity hides the truth. Stars are scattered unevenly through space. Some are relatively close. Others are so far away that their light began travelling long before Earth existed. The nearest star system to the Sun is Alpha Centauri. It is not a single star, but a group of 3 bound together by gravity. The closest of these, Proxima Centauri, holds the title of nearest known star to our solar system. The distance to Proxima Centauri is about 4.2 light-years. That phrase, light-year, does not describe time, it describes distance. 1 light-year is how far light travels in 1 year, moving at its constant speed through empty space. To put that in perspective, light travels from the Sun to Earth in 8 minutes, from the Sun to Neptune in about 4 hours, from the Sun to the outermost edges of the solar system in days or months. To reach Proxima Centauri, light travels for more than 4 years without slowing down. That is the jump in scale that occurs when leaving the Sun behind. 4 years does not sound overwhelming in everyday terms. It might be the length of a degree program or the time between major life changes. But when that span represents uninterrupted travel at the fastest speed possible, it becomes something else entirely. If a spacecraft were launched from Earth toward Proxima Centauri using current technology, it would take tens of thousands of years to arrive. Even concepts involving advanced propulsion stretch travel times into centuries. The distance is not just large, it is prohibitive. Between the Sun and the nearest stars lies interstellar space. This region is often imagined as completely empty, but that is only partly true. It contains thin gas, dust, cosmic rays and magnetic fields. The density is extremely low, far lower than the best vacuums created on Earth, but it is not zero. Still, this space offers no landmarks, no planets, no bright objects marking progress. A spacecraft travelling through it would see the Sun slowly fade behind, and the stars ahead remain stubbornly distant. From within the solar system, the nearest stars feel abstract. From interstellar space, they become destinations defined almost entirely by patience and endurance. Proxima Centauri itself is a red dwarf star. Smaller and cooler than the Sun, it emits far less light. If it replaced the Sun in our sky, Earth would freeze. Its dimness makes its proximity surprising. It is close, yet barely visible without a telescope. This highlights another important feature of cosmic scale. Near does not mean bright. Far does not mean faint. Appearance and distance are not directly linked. The light from Proxima Centauri that reaches Earth tonight began its journey before many current technologies existed. It crossed 4 light-years of space, passing through regions shaped by galactic forces, before finally arriving here. And Proxima Centauri is only the first step. The next nearest stars lie slightly farther away. Barnard's star, Wolf 359, Lalande 21185. Each sits within a bubble of space measured in single-digit light-years. These stars form what might be called the Sun's local neighbourhood. This neighbourhood is sparse. On average, stars in our region of the Milky Way are separated by several light-years. If the Sun was scaled down to the size of a grain of sand, the nearest stars would be kilometres away. That separation is fundamental to understanding the size of the universe. Galaxies are not crowded collections of stars brushing past one another. They are vast volumes where stars drift through mostly empty space, bound loosely by gravity but rarely interacting directly. From Earth, the sky hides this emptiness. Stars appear adjacent because distance collapses visually. In reality, they are isolated points separated by gulfs of nothing. Leaving the Sun behind also means leaving behind the sense of orbital order that define the solar system. Around the Sun, planets follow predictable paths. Their motions are stable over long timescales. Interstellar space is different. Stars move relative to one another. Their paths curve through the galaxy, influenced by its overall mass distribution. Over millions of years, stellar neighborhoods change. Stars that are close now will drift apart. Others will move closer. The Sun itself is moving through the Milky Way at about 220 kilometers per second. It completes one orbit around the galactic center roughly every 230 million years. During that time, it passes through different regions, encountering new stellar neighbors. So the nearest stars today are not permanent companions, they are temporary neighbors in a slow cosmic flow. Understanding this motion helps ground the idea of distance. The 4 light-years to Proxima Centauri are not static. They change slowly as both stars move through space. Distance in the universe is dynamic, not fixed. As attention lingers on the nearest stars, another shift occurs. The solar system begins to feel small, not because it has shrunk, but because the frame of reference has expanded. The solar system's diameter, even including the distant Oort cloud, is measured in fractions of a light-year. The distance to the nearest star is several times larger than that entire structure. Everything that once felt expansive now fits into a much smaller conceptual box. This does not diminish its complexity or significance. It simply places it within a larger context. From the perspective of the nearest stars, the Sun is unremarkable. It is one among many, a middle-aged star of average size in an unexceptional region of the galaxy. It does not stand out by brightness or mass. That ordinariness is important. It suggests that the processes that shape the solar system are not unique. Other stars likely host planets. Some of those planets may resemble Earth in size, composition, or temperature. Distance, not rarity, is the main barrier to knowing. This realization often brings attention to the idea of habitability beyond Earth. But for now, it serves a different purpose. It reinforces scale. The nearest stars are so far away that even knowing they exist does not make them feel reachable. They sit at the edge of what feels possible with current understanding. Yet compared to the rest of the galaxy, even these distances are small. The Milky Way is about 100,000 light-years across. That means the distance to the nearest star is only a tiny fraction of the galaxy's diameter. If the galaxy was scaled to the size of a continent, the Sun's neighborhood would fit within a small town. This layering of scale can feel destabilizing. Each time the mind adjusts to a new size, that size becomes the baseline for something larger. The process repeats without end. Leaving the Sun behind introduces the first truly interstellar distances. Light-years replace minutes and hours. Travel times stretch beyond lifetimes. Familiar reference points disappear. But the nearest stars also offer continuity. They are still stars. They still shine by nuclear fusion. They still follow physical laws that are well understood. The universe has not yet become alien. It has simply grown. This growth happens quietly. There is no dramatic boundary crossed. No moment where space suddenly feels infinite. Instead, there is a gradual accumulation of distance until the original anchor no longer dominates. At this stage, it becomes possible to imagine the Sun not as the center, but as a participant. One star among many, moving within a larger structure that holds them all. That structure is the Milky Way galaxy. Before fully stepping into it, it's worth letting the idea of interstellar distance settle. 4 light-years, 10 light-years, dozens. Each number represents years of travel for light, centuries or millennia for spacecraft, and an emptiness that resists visualization. The nearest stars teach an essential lesson. The universe does not scale smoothly from the familiar to the vast. It stretches abruptly. It inserts gaps that cannot be crossed casually. When the Milky Way first enters the conversation, it often does so as an image rather than a structure. A pale band stretching across the night sky. A faint river of light visible only when the air is clear and artificial lights are few. From Earth, it looks delicate, almost fragile, as if it could be brushed away by a passing cloud. That appearance is misleading in nearly every possible way. The Milky Way is not a cloud, not a surface, and not a background decoration. It is a galaxy. A gravitationally bound system containing hundreds of billions of stars along with planets, gas, dust, dark matter and radiation, all moving together through space. What you see from the ground is not the whole of it, but a cross-section viewed from the inside. Understanding the Milky Way requires another adjustment in perspective. Up to now, distance has been something you move through mentally, stepping outward from Earth to the Moon, then to the Sun, then past the nearest stars. With the galaxy, the scale stops being linear in any intuitive sense. You're no longer travelling from one object to another. You're embedded within a vast structure that surrounds you on all sides. The Milky Way has a flattened disc-like shape with a central bulge. Imagine a spinning disc, thicker in the middle and thinner toward the edges. Spiral arms extend outward from the centre, loosely defined regions where stars, gas and dust are more concentrated. The Sun is located within one of these arms, not near the centre, but not at the extreme edge either. Roughly 2/3 of the way out from the galactic core. From this position, the galaxy does not appear as a neat spiral. It appears as a band because you are looking along the plane of the disk. In some directions, your line of sight passes through thousands of light-years of stars. In others, it exits the disk more quickly, revealing darker regions of space. This is why the Milky Way looks brighter and denser in some parts of the sky than others. Toward the galactic centre, the density of stars increases dramatically. Toward the outskirts, it thins. Dust lanes obscure parts of the view, blocking visible light and creating dark patches that once puzzled early astronomers. The galaxy's size is difficult to hold in mind because there is no familiar comparison. The Milky Way is about 100,000 light-years across. That number does not mean 100,000 years of travel at ordinary speeds. It means 100,000 years of travel at the speed of light. A beam leaving one edge of the galaxy would still be travelling long after all recorded human history had passed. From one side of the galaxy to the other, light takes longer to travel than modern humans have existed as a species. The thickness of the galactic disk is smaller by comparison, roughly 1,000 light-years. Even so, that thickness alone is enough to contain entire stellar neighbourhoods, stacked above and below the Sun's position. The Sun is not exactly in the middle plane of the disk. It oscillates slightly above and below as it orbits the centre, completing a gentle vertical wave over tens of millions of years. That orbit itself is another marker of scale. The Sun takes about 230 million years to complete one full revolution around the galactic centre. Since its formation roughly 4.5 billion years ago, it has completed only about 20 such orbits. Dinosaurs appeared and vanished during a fraction of a single galactic year. This slow, stately motion contrasts sharply with the speed at which the Sun travels through space. At about 220 kilometers per second, the solar system is moving fast by everyday standards. Yet against the size of the galaxy, that speed produces only gradual change. The galactic centre lies about 26,000 light-years from Earth. In that direction, hidden behind thick clouds of dust, resides a supermassive black hole known as Sagittarius A. Its mass is millions of times that of the Sun. It does not dominate the galaxy in the way planets dominate their orbits, but it anchors the central region gravitationally. Stars near the core orbit more quickly. Stars farther out, like the Sun, move more slowly. The entire galaxy rotates, though not like a solid object. Different regions move at different speeds, held together by gravity and something else that does not emit light. That something else is dark matter. Dark matter does not interact with light. making it invisible to telescopes. Its presence is inferred through its gravitational effects. Without it, the Milky Way would not hold together as it does. Stars in the outer regions would move too fast and escape. Instead, they remain bound, suggesting a massive halo of unseen matter surrounding the visible galaxy. This halo extends far beyond the luminous disk. It is roughly spherical and vastly larger than the region where stars are concentrated. In terms of mass, dark matter outweighs ordinary matter by a significant margin. In terms of experience, it is undetectable except through its influence. This means that what you see when you look at the Milky Way is only a small fraction of what is actually there. The visible galaxy, the island of light, floats within a much larger, darker structure. Stars trace out only the brightest parts of a deeper gravitational landscape. The idea of the Milky Way as an island is not accidental. Galaxies are separated by immense distances, much larger than the distances between stars within them. From one galaxy to another, light travels for millions of years. In that sense, each galaxy is its own isolated region of structure, surrounded by vast expanses of relatively empty space. Within the Milky Way, stars are numerous but far apart. The average separation between stars in the Sun's neighbourhood is several light years. Even in denser regions, collisions between stars are extraordinarily rare. Space within galaxies is mostly empty, despite appearances. This emptiness allows galaxies to pass through one another during collisions without stars actually hitting. When galaxies merge, their structures distort, gas clouds compress, star formation increases, but individual stars largely pass by each other unscathed. The Milky Way itself is on a slow collision course with the Andromeda Galaxy, our nearest large neighbour. In about 4 billion years, the two will merge, reshaping both into a single, larger galaxy. From Earth's current perspective, Andromeda appears as a faint smudge, barely visible to the naked eye under ideal conditions. That faint smudge contains over 1 trillion stars. This comparison reinforces the deceptive nature of appearance. Brightness does not correspond directly to size or importance. Distance dims even the larger structures. From inside the Milky Way, it is difficult to see the galaxy as a whole. Dust obscures large portions of the disk, especially in visible light. To overcome this, astronomers use radio waves, infrared observations, and precise measurements of stellar motion. Piece by piece, a map emerges. That map shows spiral arms named for constellations and features rather than strict boundaries. The Sun resides in a smaller arm segment often called the Orion Arm or Orion Spur. It is not one of the galaxy's primary arms, but a bridge between them. This placement has no special significance beyond circumstance. The Sun did not choose its location. It formed from a cloud of gas and dust that happened to collapse here. Over time, it has drifted relative to other stars, participating in the slow churn of the galaxy. That churn is not chaotic. It follows patterns shaped by gravity, density waves, and long-term stability. Spiral arms are not rigid structures. They're regions where material bunches up temporarily, triggering star formation before dispersing again. Stars move in and out of these regions over millions of years. The Milky Way is not frozen. It is dynamic, evolving, and responsive to internal and external influences. Supernova explosions enrich the interstellar medium with heavier elements. Stellar winds carve out bubbles of hot gas. New stars ignite while others fade into remnants. Over cosmic timescales, the galaxy recycles its material repeatedly. From Earth, none of this motion is visible directly. The stars appear fixed relative to one another because the changes are slow and distances are vast. But precision measurements reveal subtle shifts, proper motions and velocity differences that confirm constant movement. The Milky Way is not a backdrop, it is an active environment. Understanding the galaxy's size also means recognizing its limits. The luminous disk extends about 50,000 light-years from the center in each direction. Beyond that, stars become sparse. The dark matter halo continues, but visible structure fades. If you were to travel outward from the Sun toward the galactic edge, you would pass through regions where stars thin out, where gas clouds become rarer, and where the night sky would grow darker rather than brighter. The Milky Way does not end abruptly. It dissolves gradually into intergalactic space. That dissolution is important. It shows that even galaxies do not have sharp borders. Like atmospheres and gravitational fields, they fade. This fading challenges the idea of an edge in the traditional sense. The galaxy has an extent, but not a wall. Its influence weakens with distance until it blends into the background of the universe. From within the Milky Way, the sky is full of stars. From far outside, the galaxy would appear as a luminous spiral suspended in darkness. Both views are correct. They are simply taken from different positions. The Milky Way has existed for over 13 billion years. It formed early in the universe's history and has grown through mergers with smaller galaxies. Evidence of these past events remains in the motions of stars and in streams of debris still orbiting the galactic centre. Some of the stars you see in the night sky may not have formed in the Milky Way at all. They may be immigrants from galaxies long since absorbed. Their presence is a quiet record of cosmic history. From Earth, these stories are invisible. Stars look the same regardless of origin, but their motions carry memory. This idea extends scale into time as well as space. The Milky Way is not just large, it is old. Its structure reflects billions of years of accumulation, interaction, and change. And yet, despite all of this, the Milky Way is only one galaxy among many. As attention lingers on its size, its complexity, its quiet dominance of our sky, it becomes tempting to treat it as the universe itself. For much of human history, that was exactly what people did. The Milky Way was thought to contain everything. Only in the last century did it become clear that those faint smudges seen through telescopes were not nearby clouds, but distant galaxies, each comparable in size to our own. That realization multiplied the universe overnight. Before stepping into that wider view, it helps to stay with the Milky Way just a bit longer, to let its scale settle, to recognize that everything encountered so far, Earth, the Moon, the Sun, the nearest stars, all reside within this single structure. This island of light feels enormous because it is, but it is also finite, bounded, and surrounded by much more. Once the idea of a galaxy as a single object becomes familiar, the next expansion becomes unavoidable. If this much space and matter can exist within one galaxy, what happens when you begin counting galaxies instead of stars? Once the Milky Way becomes familiar as a structure rather than a backdrop, something important breaks. The distances involved stop cooperating with the units that carried us this far. Kilometers failed long ago. Astronomical units became clumsy beyond the outer planets. Even light hours and light days begin to feel cramped once attention stretches across a galaxy tens of thousands of light years wide. At that point, distance stops being something you imagine travelling across and starts becoming something you measure indirectly. You no longer ask, how far would I have to go? You ask instead, how long has this light been travelling to reach me? This is where the universe quietly changes the rules. Light is no longer just illumination. It becomes the medium through which distance, history, and structure are all revealed at once. When distances grow large enough, space and time stop being separable in any intuitive way. To see far away is to see long ago. To measure size is to measure delay. This shift does not happen suddenly, but it becomes unavoidable once you move beyond the Milky Way's immediate scale. Within the galaxy, light years are useful but still feel manageable. 4 light years to the nearest star, 26,000 to the galactic centre, 100,000 across the disk. Large, yes, but still tied to a single structure, a single gravitational system. The moment you begin thinking about what lies beyond, even those numbers stretch thin. The nearest large galaxy to the Milky Way, Andromeda, is about 2.5 million light-years away. That phrase carries an enormous amount of information in a very compact form. It means the light reaching your eyes tonight left Andromeda when early humans were first learning to use stone tools. It means the photons arriving now have crossed intergalactic space for longer than our species has existed. 2.5 million years is not a number that fits comfortably into human thinking. It is not tied to any lived experience. It exceeds recorded history by a factor of hundreds. Yet in cosmic terms, it is a short distance. Andromeda is close. This is one of the recurring disorientations of astronomy. Distances that overwhelm human perspective are treated as local, nearby, and immediate when viewed against the full scale of the universe. Once galaxies enter the picture, light years stop being impressive and start being minimal. Astronomers switch to millions, then billions of light years as a matter of routine. Not because they enjoy large numbers, but because nothing smaller will do. At these scales, light itself becomes the only ruler that makes sense. If you try to describe the distance between galaxies using kilometers, the numbers would be so large they would lose all meaning. If you try to imagine traveling those distances, the exercise would collapse under its own weight. Light offers a way out of this problem. It provides a consistent universal measure that works everywhere and does not depend on local conditions. Light does not care about gravity fields in the same way objects do. It does not slow down in empty space. It travels at the same speed whether it is near Earth, near a star, or drifting through the void between galaxies. That reliability makes it invaluable. More importantly, light carries information. Every photon that reaches a telescope brings with it a record of where it came from and when. Its colour reveals motion through redshift or blueshift. Its intensity hints at distance and energy. Its arrival time encodes scale. When astronomers say a galaxy is 10 billion light-years away, they are saying something very precise. They are saying that the light we see today began its journey 10 billion years ago. The galaxy itself may now be much farther away due to cosmic expansion, but the information we receive is frozen in time. This introduces a concept that takes some getting used to. When you look far enough into space, you are no longer seeing the universe as it is now. You're seeing it as it was. Nearby stars are seen almost as they are in the present. Their light left years ago, but the difference is negligible on human timescales. Distant galaxies are different. Their light left when the universe itself was younger. At a distance of 1 billion light-years, you are looking back 1 billion years. At 10 billion light-years, you are approaching the era when galaxies were still forming. At the farthest distances we can observe, you are seeing light released when the universe was only a few 100,000 years old. This means that distance is not just size, it is history. The farther out you look, the earlier the snapshot you receive. The universe does not present itself all at once. It reveals itself in layers of time stacked outward from your position. This is why switching to light as a measuring tool is not optional. It is the only way to keep track of both scale and sequence at once. The Milky Way, large as it is, occupies a single frame in this vast sequence. Beyond it lie other galaxies, grouped into clusters and superclusters, separated by spaces that make even interstellar distances look modest. Galaxies are not scattered randomly. They follow patterns shaped by gravity and the initial conditions of the universe. On the larger scales, they trace out filaments, walls, and voids, forming a structure often called the cosmic web. These structures extend for hundreds of millions of light-years. Some span over 1 billion. Light is the only way to describe them coherently. When astronomers map these structures, they do not measure from one end to the other with a tape measure. They analyze redshift, brightness, and distribution of light. Distance becomes something inferred from how light behaves rather than how space feels. Redshift plays a key role here. As the universe expands, space itself stretches. Light travelling through that expanding space gets stretched along with it, shifting towards longer wavelengths. The more distant a galaxy is, the more its light is redshifted. This relationship between redshift and distance allows astronomers to estimate how far away objects are, even when they cannot measure distance directly. Again, Light is doing the work. The fact that space itself expands adds another layer of complexity. When we say a galaxy is 10 billion light-years away, we're not saying that light has travelled 10 billion years through static space. The space between us and that galaxy has been expanding the entire time, so the galaxy was closer when the light left than it is now. The distance has grown during the journey. This means the universe is larger now than the light we see suggests. The observable universe, defined by how far light has had time to reach us since the beginning, is not the same as the entire universe. Here again, light sets the limits. There is a maximum distance from which light has had time to arrive since the universe became transparent. That boundary defines what we can observe. Beyond it, light has not yet reached us, and so information is unavailable. This boundary is often called the observable universe. Its radius is about 46 billion light-years, even though the universe itself is about 13.8 billion years old. That apparent contradiction exists because space has expanded while the light was travelling. Without using light as the reference, this kind of reasoning collapses. Light is also the reason we know the universe has a finite age. If the universe were infinitely old and static, the night sky would be bright in every direction. Every line of sight would eventually end on a star. This is known as Olber's paradox. The fact that the sky is dark tells us something profound. It tells us that the universe has not existed forever in its current form. There has been a beginning, and light from beyond a certain distance simply has not had time to arrive. Once again, light defines scale. It is tempting to think of light-years as abstract units, but they are deeply physical. They represent real travel time for real particles carrying real information. Every second that passes increases the radius of what can be observed, though not in a way that changes noticeably within a human lifetime. This slow expansion of the observable boundary is happening continuously. The universe is not revealing itself all at once. It is revealing itself gradually as light arrives from farther and farther regions. At the same time, cosmic expansion is accelerating. This means that some regions of the universe are moving away from us faster than light can reach us. Not because anything is breaking the speed limit, but because space itself is expanding. Light emitted today from those regions will never reach Earth, no matter how long we wait. Those regions are permanently beyond observation. This introduces a subtle but important distinction. There is the observable universe, defined by light that can reach us, and there is the universe beyond that, which may be much larger, possibly infinite. We do not know how large the entire universe is. We only know how large the observable portion is. This uncertainty is not a failure of measurement. It is a consequence of physics. When distances become large enough, even light cannot bridge them. Information becomes inaccessible not because of technological limits, but because of the structure of space-time itself. At this point, the idea of distance is fully detached from everyday experience. You're no longer imagining travel or motion in any intuitive sense. You're thinking in terms of horizons, delays, and limits imposed by the speed of light and the expansion of space. This is why the universe feels different once you reach these scales. It stops being something you could, in principle, cross. It becomes something you can only observe partially. The shift to light-based measurement is not just a convenience. It is an admission, an acknowledgement that human intuition has reached its limit and must be replaced by indirect understanding. And yet, even within these constraints, the universe remains structured, measurable, and consistent. Light behaves predictably. Redshift follows rules. Patterns emerge. The distances are large, but they are not arbitrary. As attention rests here, it becomes clear that everything encountered so far — Earth, Moon, Sun, Solar System, nearest stars, Milky Way — all occupy a tiny fraction of the observable universe. They are local features in a vast expanse whose size is defined not by edges we can reach, but by how long light has been travelling. This realization does not arrive with drama. It settles gradually. The mind stops trying to picture everything at once and instead accepts a layered view. Near, far, farther still, each layer revealed by older light. Once distance is understood through light rather than travel, galaxies stop being rare landmarks and start becoming the basic units of structure. This shift happens quietly. There is no single moment where the universe suddenly fills up. Instead, as instruments improve and perspective widens, galaxies simply keep appearing, one after another in every direction you look. From Earth, with unaided eyes, only a few galaxies are visible. Andromeda is the most famous. Under dark skies, it appears as a faint smudge, easily mistaken for a cloud or a trick of vision. It does not announce itself as a system containing hundreds of billions of stars. It barely announces itself at all. That faintness is not because Andromeda is small, it is because it is far away. Once telescopes are involved, the view changes dramatically. Point a modest telescope at what looks like empty sky, and points of light resolve into smudges. Increase sensitivity, and smudges multiply. Push deeper, and those smudges resolve into spirals, ellipses, distorted shapes, and glowing arcs. Each one is a galaxy. This realization took time to settle historically. For centuries, astronomers debated whether the faint objects seen through telescopes were part of the Milky Way or something else entirely. They were called nebulae, a general term for anything fuzzy and unresolved. Some of them turned out to be gas clouds within our galaxy, others did not. The turning point came when distances could finally be measured reliably. Once it became clear that some of these objects lay far beyond the boundaries of the Milky Way, the scale of the universe expanded overnight. The Milky Way was no longer the whole story. It was one example. What followed was not a neat census, but an avalanche. Galaxies appeared everywhere telescopes could see, not clustered in one direction, not concentrated around us. They filled the sky uniformly, suggesting that the universe, on large scales, looks roughly the same in every direction. This uniformity matters. It tells us something fundamental about the universe's structure. We are not in a special location. There is no central vantage point where galaxies are densest. Wherever you look, you see more of the same. That idea can feel counterintuitive. Human experience is shaped by centers. Cities have downtowns, rooms have corners, landscapes have focal points. The universe does not seem to work that way. Galaxies are distributed throughout space in a way that looks random at first glance, but is not. They trace patterns shaped by gravity and the initial conditions of the universe. On smaller scales, they cluster. On larger scales, those clusters form networks. But averaged over enormous distances, the distribution evens out. This is why astronomers sometimes say the universe is homogeneous and isotropic on large scales. Those words simply mean that it looks similar everywhere and in every direction when viewed broadly enough. From a human standpoint, this is unsettling. It removes the idea of a privileged viewpoint. There is no edge where galaxies stop on one side and pile up on another. They are quietly everywhere. The sheer number of galaxies is difficult to state without immediately losing intuition. Estimates suggest that the observable universe contains hundreds of billions, possibly trillions, of galaxies. That number has increased as telescopes have improved. Each time astronomers look deeper, more galaxies appear. The Hubble Space Telescope provided one of the clearest demonstrations of this. When it was pointed at what seemed like an empty patch of sky and left to observe for an extended period, the resulting image revealed thousands of galaxies in a region no larger than a grain of sand held at arm's length. That image was not unusual. Similar deep field observations in other directions produced similar results. Empty sky turned out not to be empty at all. It was filled with galaxies too faint and distant to be seen without long exposure. This tells us something important about scale. The universe is not just large because it extends far. It is large because it is densely populated with structure across that entire extent. Yet, densely is a relative term. Between galaxies lie enormous voids. Intergalactic space is far emptier than interstellar space. The distances between galaxies are measured in millions of light years. Even within clusters, galaxies are separated by vast stretches of nothing. This combination of abundance and emptiness is a recurring theme. There are many galaxies, but they do not crowd one another. They exist as isolated systems drifting through space, connected only by gravity and the slow expansion of the universe. Galaxies themselves come in many forms. Spiral galaxies like the Milky Way have disks, arms, and central bulges. Elliptical galaxies are more rounded, lacking distinct structure. Irregular galaxies defy simple classification, often shaped by interactions or mergers. These forms are not static. Galaxies evolve. They collide, merge, distort, and reform. Over billions of years, spirals can become ellipticals. Small galaxies can be absorbed by larger ones. New stars ignite while others fade. From Earth, this evolution is invisible in real time. The timescales are too long. But by looking at galaxies at different distances, astronomers effectively look at galaxies at different stages of life. Nearby galaxies tend to be mature. Distant galaxies often appear younger, more chaotic, more actively forming stars. This is not coincidence. It is a consequence of light travel time. When you observe a galaxy 10 billion light-years away, you're seeing it as it was 10 billion years ago. You're not looking across space alone. You're looking back into an earlier universe. This means that the population of galaxies you see at great distances is not the same population that exists today. Some have merged, some have changed shape, some no longer exist as separate entities. Distance becomes a time machine. As galaxies recede farther into the background, they also appear different in other ways. Their light is redshifted due to cosmic expansion. Their brightness decreases, their details blur. At extreme distances, individual stars cannot be resolved at all. Only the combined glow remains. Eventually, galaxies become so faint that they are barely detectable even with the most powerful instruments. Beyond that point, they disappear from view entirely, not because they are gone, but because their light has not yet reached us or never will. This gradual fading defines the limits of observation. There is no sudden cut-off. There is no visible wall where galaxies stop. They simply thin out into darkness. This has an important psychological effect. It makes the universe feel incomplete, not in structure, but in access. There is more out there than we can see, always. The idea that galaxies are everywhere does not mean they are evenly spaced like points on a grid. They are arranged in a complex pattern shaped by gravity. Clusters of galaxies form where matter is denser. Vast voids form where matter is sparse. These voids are enormous, sometimes hundreds of millions of light-years across. They are not completely empty, but compared to their surroundings, they are quiet regions with few galaxies. Between voids lie filaments and walls where galaxies line up along invisible scaffolding. This large-scale structure resembles a foam or a web. It is one of the most striking features of the universe when viewed at sufficient scale. The existence of this structure tells us that galaxies did not form randomly. Small differences in density in the early universe grew over time as gravity pulled matter together. Regions slightly denser than average attracted more matter, becoming denser still. Regions slightly emptier lost matter and became voids. Over billions of years, this process produced the cosmic web. From Earth, we do not see the web directly. We see its pieces, clusters, groups, chains of galaxies. Only by mapping large volumes of space does the pattern emerge. Again, light is the tool that makes this possible. By measuring the redshift of galaxies, astronomers determine their distances and positions in 3 dimensions. This turns points of light into a map of structure. When these maps are assembled, they reveal that galaxies are not scattered haphazardly. They follow the same underlying patterns everywhere observed. This consistency reinforces the idea that the universe operates under uniform physical laws, the same processes that shape the Milky Way-shaped distant galaxies. The same gravity that governs local motion governs the larger structures. Galaxies are quietly everywhere because the universe itself is quietly structured. From a human perspective, this abundance can feel overwhelming. It invites questions about significance, rarity, and place. But those questions arise from emotional interpretation, not physical necessity. The universe does not require a center to function. It does not require a purpose recognizable to us. It simply unfolds according to its rules, producing structure at every scale. From this viewpoint, the Milky Way becomes one among countless others, unique in detail, unremarkable in category. Earth becomes a planet orbiting a star within one galaxy among many. This realization does not erase meaning. It changes the frame. The sky, once thought to be a fixed ceiling, becomes a window. Not a window onto a single backdrop, but onto a layered expanse filled with systems upon systems, each operating independently yet shaped by common forces. When you look up now, even without a telescope, it is possible to know that behind every patch of darkness lie galaxies too faint to see. They are not hidden intentionally. They are simply far away. Their light is still travelling. Some of it has been on the move longer than any human story. Some of it will never arrive. This quiet abundance reshapes the idea of size. The universe is not just large because it stretches far in one direction. It is large because it contains vast numbers of large things, separated by distances that dwarf even those things. And still, this is not the final scale. Galaxies group together. Groups form clusters. Clusters form larger associations. Structures emerge that span hundreds of millions of light years. At that point, individual galaxies become dots in patterns too large to see all at once. Once galaxies stop being treated as isolated wonders and start being understood as common features of space, another pattern quietly comes into focus. Galaxies do not float alone forever. Gravity, patient and unassuming, draws them together over immense spans of time. The result is not chaos but structure. Large-scale structure. The kind that only becomes visible when distance is measured not in years or centuries, but in millions of light years. This is where the architecture of the cosmos begins to show itself. A single galaxy like the Milky Way is already vast beyond everyday comprehension, yet in the universe's accounting, it is a building block rather than a final form. Galaxies gather into groups, bound together by their mutual gravitational pull. These groups can contain a few galaxies or dozens. The Milky Way itself belongs to one such group, often called the local group. The local group contains more than 50 known galaxies, though most are small, faint dwarf galaxies. The two dominant members are the Milky Way and Andromeda, accompanied by Triangulum and a collection of much smaller companions. These galaxies orbit a shared centre of mass, moving slowly, interacting gravitationally, and occasionally exchanging material. From Earth, this grouping is invisible. The distances between these galaxies are so large and their motion so slow that they appear fixed relative to one another. Only through careful measurement over decades does their shared motion become apparent. The local group spans several million light years. That scale alone would have seemed impossibly large not long ago. Yet in cosmic terms, it is modest. Beyond galaxy groups lie galaxy clusters. Clusters are the largest gravitationally bound structures in the universe. They contain hundreds to thousands of galaxies, all held together by gravity, embedded in a vast cloud of hot gas and dark matter. These clusters can span tens of millions of light years from one side to the other. One of the nearest large clusters is the Virgo cluster, located about 55 million light years away. It contains over 1,000 galaxies, including massive ellipticals and spirals of every shape and size. The Milky Way is slowly moving toward this cluster, influenced by its immense mass. From Earth, the Virgo cluster appears as a region of the sky populated by many galaxies, but without context, it does not stand out as a single object. Its true size and coherence only become apparent when distances are measured and motions mapped. Clusters are not neat spheres of galaxies arranged politely in space. They are dynamic environments. Galaxies within clusters move at high speeds relative to one another, sometimes thousands of kilometers per second. Over time, they interact, merge, distort, and strip gas from one another. The space between galaxies in a cluster is filled with extremely hot gas, heated to millions of degrees by gravitational compression. This gas emits X-rays, making clusters visible in wavelengths far beyond human vision. In fact, much of a cluster's normal matter exists not in stars, but in this diffuse, superheated medium. Even more significant is the role of dark matter. Clusters contain far more mass than can be accounted for by visible galaxies and gas alone. The gravitational pull required to keep clusters bound reveals the presence of vast halos of dark matter enveloping them. In many ways, clusters are dark matter structures first, with galaxies embedded within them like lights marking an invisible framework. As clusters grow, they do not remain isolated either. Gravity operates on every scale, and clusters themselves are drawn together into larger associations known as superclusters. Superclusters are not tightly bound in the same way clusters are. They are looser collections, sprawling across hundreds of millions of light years. Within them, clusters and groups trace out elongated shapes, sheets, and filaments. The local group belongs to a supercluster often called the Laniakea supercluster. This structure spans roughly 500 million light-years and contains tens of thousands of galaxies. It is defined not by sharp edges, but by the flow of galaxies toward a common gravitational region. Within Laniakea, galaxies are moving along large-scale paths shaped by gravity, converging toward a region known as the Great Attractor. This region exerts a subtle but measurable influence on the motion of galaxies across vast distances. The existence of superclusters reveals that the universe is not a random scattering of matter. It is organized on scales far larger than individual galaxies. Yet even superclusters are not the largest structures present. When astronomers began mapping galaxy positions across truly enormous volumes of space, a striking pattern emerged. Galaxies and clusters are arranged along vast filaments, intersecting at dense nodes, surrounding immense empty regions called voids. This pattern is known as the cosmic web. The cosmic web is not made of matter in the usual sense. It is a large-scale distribution pattern, shaped primarily by dark matter and gravity. Ordinary matter falls into this framework, collecting where dark matter density is highest, forming galaxies and clusters along the filaments. These filaments can stretch for hundreds of millions of light years. Some walls of galaxies extend for over 1 billion light years. Between them lie voids that are comparably vast, regions where very few galaxies exist. From a human perspective, this scale is almost impossible to visualize. Entire superclusters can fit inside a single filament. Entire galaxies become points along threads too long to see end to end. Yet this structure is not chaotic. It follows from simple rules applied over immense time. Small variations in density in the early universe grew under gravity's influence. Slightly denser regions pulled in more matter, becoming denser still. Slightly emptier regions lost matter and became voids. Over billions of years, this process sculpted the large-scale architecture we observe today. The cosmic web is not something you could ever see from a single location. It only becomes visible through extensive surveys that measure the positions and distances of millions of galaxies. Each galaxy adds one data point. Together they reveal the pattern. When these maps are constructed, they show remarkable consistency. No matter which direction astronomers look, the same web-like structure appears. Filaments, nodes, voids, repeating across the observable universe. This uniformity supports the idea that the universe follows the same physical laws everywhere. There are no special regions where structure behaves differently. The same processes play out on all observable scales. Galaxy clusters serve as anchors within this web. They sit at intersections of filaments, where matter has accumulated most densely. These nodes are sites of intense gravitational activity, where galaxies form, interact and evolve rapidly compared to more isolated regions. In contrast, galaxies located in voids evolve more quietly. With fewer interactions and less surrounding material, they change more slowly. Environment matters, even on cosmic scales. The existence of voids is as important as the presence of clusters. Voids define the space between structures. They're not truly empty, but they contain far less matter than average. Their sheer size contributes significantly to the universe's overall scale. Some voids span hundreds of millions of light years. To cross one at the speed of light would take longer than the entire recorded history of human civilization, and yet, voids are common. This interplay between dense regions and vast emptiness gives the universe its texture. It is neither uniformly filled nor sparsely scattered. It is structured. From Earth, this architecture is hidden. The sky looks smooth. Galaxies appear as isolated smudges. Without distance information, depth disappears. Everything collapses into a two-dimensional shell. Only by switching fully to light-based measurement does the third dimension emerge. Redshift reveals distance. Distance reveals structure. Structure reveals scale. At this point, the idea of the size of the universe becomes less about a single number and more about layers of organization. Galaxies form clusters. Clusters form superclusters. Superclusters trace filaments. Filaments surround voids. All of it fits within the observable universe, and still, the observable universe may be only a portion of the whole. The architecture we see does not necessarily extend infinitely in the same way. Beyond the observable horizon, there may be more filaments, more voids, more clusters arranged in similar patterns, or there may be something different. We cannot know directly. What we can say is that within what we can observe, structure persists up to the larger scales measured. There is no sign yet of an edge where organization stops and randomness begins. This realization changes how size is understood. The universe is not just a container filled with objects. It is a network, a framework, a system of relationships shaped by gravity and time. Each increase in scale does not erase what came before. It incorporates it. Earth sits within the solar system. The solar system moves among stars. Stars form a galaxy. Galaxies gather into clusters. Clusters assemble into superclusters. Superclusters trace the cosmic web. At no point does the process break. It simply continues. By the time the universe is viewed through the lens of clusters and superclusters, it becomes clear that galaxies are not scattered like grains of sand across an empty floor. They are arranged. Not deliberately, not neatly, but unmistakably. The arrangement is subtle at first, easy to miss when looking at only a small patch of sky. It only reveals itself when distances are measured across truly vast scales, and when patience allows patterns to emerge from what initially looks like randomness. This arrangement is what astronomers call the cosmic web. The name can sound dramatic, but the idea behind it is straightforward. Matter in the universe is not evenly distributed. It gathers where gravity pulls it, and it avoids regions where gravity is weaker. Over billions of years, this uneven pull has shaped matter into long, thin structures surrounded by enormous empty regions. Galaxies trace these structures like light strung along invisible threads. From Earth, none of this is obvious. The sky does not show threads or voids. It shows points of light flattened against darkness. Depth is hidden. Distance is compressed. The web only becomes visible when three-dimensional maps of the universe are constructed using light as a ruler. When astronomers began plotting the positions of thousands, then millions of galaxies, a striking pattern appeared. Galaxies clustered along elongated filaments. These filaments intersected at dense nodes, where galaxy clusters formed. Between the filaments lay vast regions with very few galaxies at all. These empty regions are called cosmic voids. Voids are not small gaps. They're among the largest known structures in the universe. Some span tens of millions of light years, others stretch across hundreds of millions. Compared to the filaments and clusters around them, they contain very little matter. Galaxies inside voids are rare and often isolated. The filaments themselves can be equally vast. Some extend for hundreds of millions of light years, connecting clusters across enormous distances. They are not solid structures. They are regions where matter density is slightly higher than average, enough to guide the formation and motion of galaxies over time. Together, filaments, nodes, and voids form a web-like pattern that fills the observable universe. This web is not made of strings or fibers in any literal sense. It is a statistical pattern, an emergent structure that arises when gravity acts on matter over long periods. The threads are traced by galaxies, gas, and dark matter, all responding to the same underlying forces. Dark matter plays a central role here. Ordinary matter, the kind that makes up stars, planets, and people, accounts for only a small fraction of the universe's total mass. Dark matter outweighs it by a factor of roughly 5 to 1. It does not emit light, absorb it, or reflect it. Its presence is known only through gravity. In the early universe, tiny fluctuations in the density of dark matter provided the scaffolding for everything that followed. Where dark matter was slightly denser, gravity pulled in more matter. Over time, these regions grew denser still, drawing in gas that eventually formed stars and galaxies. The visible cosmic web is essentially ordinary matter settling into a structure defined by dark matter. This explains why filaments are not sharply defined objects. They are regions where the density of matter is higher than average, not rigid boundaries. Galaxies move along these filaments, drawn toward nodes where gravity is strongest. Clusters of galaxies sit at these nodes. They are the intersections of filaments, places where matter has accumulated most efficiently. Voids lie between them, regions that lost matter early on and never recovered it. The scale of this structure is difficult to grasp because it does not have a familiar counterpart. There is nothing in everyday life that resembles a network hundreds of millions of light years across, composed of mostly empty space and a few dense knots of matter. Even on Earth, the largest networks, transportation systems, power grids, ecosystems, are tiny by comparison. They exist within a narrow range of distances. The cosmic web spans scales that dwarf entire galaxies. One way to approach this is to step back mentally and consider how much space is actually involved. A typical filament may be several million light-years thick and hundreds of millions long. That thickness alone is enough to contain dozens of Milky Way-sized galaxies side by side. Yet within those filaments, galaxies remain far apart. Even in the densest regions, space is mostly empty. The web is not crowded, it is sparse. This sparsity is essential. If matter were packed tightly everywhere, the universe would look very different. Stars would collide, galaxies would merge constantly, stable planetary systems would be rare. The web structure allows complexity to exist without constant disruption. The voids are equally important. They define the space between structures and contribute significantly to the universe's overall volume. In fact, most of the universe's volume is taken up by voids, not by galaxies or clusters. From a distance, this means the universe looks more empty than full. Matter is concentrated into relatively thin regions, leaving vast expanses with almost nothing in them. This distribution has observable consequences. Light travelling through voids behaves differently than light passing through dense regions. Gravitational lensing, where massive structures bend light, is stronger near clusters and filaments. Voids produce subtle lensing effects of their own, slightly stretching images in the opposite direction. By studying these effects, astronomers can map the distribution of matter, including dark matter, across large scales. Once again, light serves as both messenger and measuring tool. The cosmic web also evolves over time. It did not always look the way it does now. In the early universe, matter was distributed more evenly. Over billions of years, gravity amplified small differences, pulling matter into filaments and clusters and evacuating voids. When we observe very distant galaxies, we see the web in an earlier stage of development. Filaments are present but less pronounced. Clusters are smaller and less settled. Voids are less empty. This gradual sharpening of structure is one of the clearest pieces of evidence for how the universe has evolved. It shows that the web is not static. It is the product of ongoing processes playing out over immense spans of time. Another important feature of the cosmic web is that it appears consistent in every direction observed. Large surveys of galaxies show similar filamentary patterns no matter where astronomers look. This suggests that the web is a universal feature of the observable universe, not a local anomaly. This consistency supports the idea that the same physical laws govern the universe everywhere. Gravity behaves the same way, matter responds the same way. Structure forms the same way. There is no sign that the universe changes its rules at large distances. The web also places limits on how large individual structures can be. Filaments and walls grow until they reach a scale where cosmic expansion begins to dominate over gravity. Beyond that, matter cannot easily collapse into larger structures. This sets an upper bound on the size of coherent structures in the universe. While filaments can be hundreds of millions of light-years long, they do not extend indefinitely. They are part of a larger pattern that repeats without forming a single, all-encompassing object. In this sense, the cosmic web represents the largest level of organization in the universe that we currently observe. Beyond it, the universe appears statistically uniform. No larger patterns have been found. When averaged over very large volumes, the distribution of matter smooths out. This transition from structured to uniform is another subtle boundary. It does not mark the end of the universe, but it marks the limit of recognizable architecture. Within that limit, the web connects everything. The Milky Way is not isolated in empty space. It sits within a filament of the cosmic web, part of a chain of galaxies extending across tens of millions of light-years. That filament connects to others, forming the larger supercluster environment discussed earlier. Earth, by extension, is part of this web. Not directly, not meaningfully in daily life, but physically. The atoms here exist within matter that traces one thread of a structure spanning a significant fraction of the observable universe. This connection is easy to overlook because it does not affect everyday experience. Gravity from distant clusters does not pull noticeably on you. Light from faraway galaxies does not illuminate your room. The web operates at scales far removed from human concerns, but its existence reshapes the idea of separation. Objects in the universe are not just scattered independently, they are related through shared structure and history. The path matter took from the early universe to form stars, planets, and people is part of the same process that shaped filaments and voids. The web is a record of that process. It encodes information about the universe's initial conditions, its composition, and its expansion history. By studying the shape and distribution of the web, astronomers test theories about dark matter, dark energy, and the overall geometry of the universe. Small changes in these parameters would produce noticeably different web structures. The fact that observations match predictions closely gives confidence that our understanding, while incomplete, is on the right track. Still, there are open questions. The exact nature of dark matter remains unknown. The role of dark energy in shaping large-scale structure is still being explored. The web may hold clues to both. As attention rests on this vast network, the sense of size becomes more diffuse. There is no single object to focus on, no central landmark. Instead, size is expressed through repetition and extent. filaments stretch on, voids open wide. Patterns continue beyond the limits of individual maps. The universe begins to feel less like a collection of things and more like a connected whole. At the same time, limits start to appear again. Not limits of structure, but limits of observation. The web we see is the web that light has had time to reveal. Beyond that, there may be more threads, more voids, more clusters arranged in similar ways. Or there may be something different. We do not know, because light from those regions has not reached us. The web, as vast as it is, exists within a boundary defined by time and expansion. This brings the question of size back into focus. The universe is not just large because it contains many things. It is large because it contains structure across immense distances, connected in ways that only become visible when space is measured using light itself. And even that visible structure may be only part of a much larger whole. With the cosmic web in view, attention naturally shifts toward the idea of boundaries. How far does this structure extend? Is there an edge to what can be seen? And what does it mean to talk about an edge in a universe where structure fades rather than stops? After wandering through stars, galaxies, clusters, and the vast lattice of the cosmic web, the question of size quietly shifts again. It is no longer just about how much exists, or how far structures extend. It becomes something more restrained, more subtle. How far can we actually see? This question sounds modest, almost practical, but it reaches deeper than it first appears. It is not asking about eyesight or telescope power alone. It is asking about the limits imposed by the universe itself. Limits set not by technology, but by time, motion, and the fundamental behavior of light. When you look up at the night sky, it feels as though you are seeing everything that is out there. Darkness sprinkled with stars, a few galaxies if conditions are right. It feels complete. But that sense of completeness is an illusion created by human scale. In reality, what you're seeing is only a thin shell of information that happens to have arrived here. Everything visible in the universe is visible for one reason only. Light from it has had enough time to reach us. That simple statement carries enormous consequences. Light does not travel infinitely fast. It moves at a fixed speed, the same everywhere, without exception. Because of that, the universe has a built-in delay. The farther away something is, the longer its light takes to arrive. At small distances, that delay barely matters. At large distances, it becomes the defining feature. This means there is a limit to what can be seen, regardless of how powerful a telescope becomes. Some light simply has not arrived yet. Some never will. The universe is about 13.8 billion years old. That number is not an estimate pulled from thin air. It comes from multiple independent lines of evidence, including the expansion rate of space, the properties of the oldest stars, and the faint glow left over from the early universe itself. If the universe has existed for 13.8 billion years, then in the simplest possible picture, light could not have travelled farther than 13.8 billion light years. That would seem to define the edge of visibility. But the universe is not simple in that way. Space itself has been expanding the entire time light has been travelling. While light moves through space, the space it moves through stretches. This stretching increases the distance between where the light started and where it ends up. As a result, the region we can observe today is much larger than 13.8 billion light years in radius. The observable universe has a radius of about 46 billion light years. This is one of the most counterintuitive facts in cosmology. How can something be 46 billion light years away in a universe that is only 13.8 billion years old? The answer lies in the expansion of space. Light did not travel through static space. The space expanded underneath it. So when we talk about how far we can see, we are not talking about a simple sphere defined by light speed multiplied by time. We are talking about a dynamic boundary shaped by expansion. This boundary is called the particle horizon. It marks the greatest distance from which light has had time to reach us since the universe became transparent. That last phrase matters. The universe was not always transparent. In its earliest moments, the universe was hot, dense, and opaque. Matter and radiation were tightly coupled. Light could not travel freely because it was constantly scattered by charged particles. The universe was filled with a glowing fog. About 380,000 years after the beginning, the universe cooled enough for electrons and protons to combine into neutral atoms. Once that happened, light could finally move freely. Space became transparent. The light released at that moment has been travelling ever since. Today we detect it as the cosmic microwave background, a faint glow that fills the sky in every direction. It is not coming from one place. It is coming from everywhere at once, from the surface where the universe first became transparent. This glow marks the farthest distance we can see in any direction. It is not an edge in space, it is an edge in time. Beyond that surface, light has not reached us because light could not travel before that point. The universe existed earlier, but it was opaque. Information from before that time is inaccessible using light. So when we ask how far we can see, the answer is layered. We can see nearby stars almost as they are now. We can see distant galaxies as they were billions of years ago. And we can see the afterglow of the early universe as it was when it first became visible. Beyond that, we cannot see at all. This does not mean there is nothing beyond that boundary. It means there is nothing we can observe directly with light. The distinction is crucial. The observable universe is not the entire universe. It is the portion of the universe from which light has reached us. The total universe may be much larger. It may even be infinite. Current observations cannot rule that out. This limitation is not something future technology will overcome easily. No matter how powerful a telescope becomes, it cannot collect light that has not arrived. It cannot see past the cosmic horizon. The horizon itself is not fixed, it evolves over time. As the universe ages, light from slightly farther regions has time to arrive. However, cosmic expansion complicates this picture. The expansion of the universe is accelerating. This acceleration is driven by something called dark energy, a property of space that causes distant regions to recede from us faster and faster. Because of this acceleration, there are regions of the universe whose light will never reach us, no matter how long we wait. They are moving away from us too quickly, carried by the expansion of space itself. This creates an event horizon. Beyond it, events are permanently unobservable. So there are two relevant limits. One marks how far we can see now. The other marks how far we will ever be able to see. These horizons are not walls. They do not mark abrupt changes. They are smooth boundaries defined by the flow of time and space. From a human perspective, this can feel unsettling. There are parts of the universe that exist that may contain galaxies, stars, perhaps planets, but whose light will never reach Earth. They are causally disconnected from us. No signal sent from here will ever reach them either. This does not mean the universe is fractured or incomplete. It means it is larger than the portion we can access. Understanding this helps reframe the idea of size. The universe is not something we can survey completely. It is something we sample from one location within it. Every observation is local. Even the most distant galaxies are observed from here, from now, with light that has travelled under specific conditions. This introduces an unavoidable bias. We see only what the universe allows us to see. Astronomers account for this carefully. They use statistical methods, models, and simulations to infer what lies beyond observation. They compare different regions of the sky to test whether the observable universe is representative of the whole. So far, the evidence suggests that the observable universe is fairly typical. There are no obvious signs that we live in a special region. The distribution of galaxies looks similar in all directions. The cosmic microwave background is remarkably uniform, with only tiny fluctuations. This uniformity supports the idea that the universe extends far beyond what we can see, maintaining similar properties on scales larger than the observable horizon. But certainty remains out of reach. The question, how far can we actually see, also depends on wavelength. Visible light is only one small part of the electromagnetic spectrum. The universe emits radiation across a wide range of energies, from radio waves to gamma rays. Some wavelengths travel more easily through dust and gas. Infrared light, for example, can pass through regions that block visible light. Radio waves can travel even farther. By observing the universe in multiple wavelengths, astronomers can peer deeper into dusty regions and uncover objects that would otherwise remain hidden. However, no wavelength can overcome the fundamental horizons set by time and expansion. All forms of electromagnetic radiation are subject to the same speed limit. There are other messengers besides light. Neutrinos and gravitational waves can travel through regions opaque to light. They offer glimpses into events and epochs inaccessible to electromagnetic observation. Even so, they too face limits imposed by cosmic expansion. They cannot deliver information from beyond the event horizon. So the picture remains consistent. There is a boundary to what can be known directly. This boundary is not static in appearance. As you look outward, objects gradually fade. Galaxies become smaller, redder, and harder to resolve. Eventually they blur into a diffuse background, then even that disappears. At the farthest distances, the universe transitions from structured to smooth. Individual galaxies are no longer visible, only the faint afterglow of the early universe remains. That afterglow is astonishingly uniform. Its temperature varies by only 1 part in 100,000 across the entire sky. Those tiny variations encode the seeds of all later structure. Slightly denser regions became filaments and clusters. Slightly less dense regions became voids. The fact that we can measure these variations at all is a testament to how far observation has come. Yet even this achievement carries a reminder of limits. The cosmic microwave background does not show us the beginning itself. It shows us the earliest moment light could travel freely. Before that, the universe is hidden from direct view. So how far can we actually see? We can see out to the cosmic horizon, about 46 billion light-years in every direction. We can see galaxies as they were billions of years ago. We can see the universe when it was young, hot, and simple. We cannot see beyond that. We cannot see the entire universe. We cannot see how far it truly extends. This realization can be interpreted in different ways. It can feel restrictive, as though something essential is out of reach. Or it can feel humbling, a reminder that existence is larger than perception. It also reframes the meaning of observation itself. Seeing is not just about looking. It is about receiving information that has survived a long journey through an evolving universe. Every photon collected by a telescope carries history. It tells a story about where it came from and when. It also tells a story about what happened to it along the way, stretched by expansion, bent by gravity, scattered by matter. To see far is to see old. The night sky, then, is not a snapshot. It is a collage of moments. Nearby stars are seen almost as they are now. Distant galaxies are seen as they were long ago. The cosmic background shows a universe before stars existed at all. All of this is visible at once, layered by distance. Understanding how far we can see also clarifies how small our window is. 13.8 billion years sounds long, but compared to eternity, it is brief. Compared to the potential size of the universe, it is tiny. The observable universe may be just a patch within something far larger, or it may be the whole. Current physics cannot decide between these possibilities definitively. What can be said with confidence is that size, at the larger scales, is not something we experience directly. It is something we infer. An inference always carries uncertainty. This uncertainty is not a flaw. It is a feature of honest inquiry. It acknowledges the difference between what exists and what can be known. As this idea settles in, the notion of an edge becomes less concrete. There is no cliff at the end of space. There is a horizon defined by time and motion. Beyond that horizon, the universe continues, or perhaps does not, in ways we cannot currently verify. Once the limits of observation are understood, the next question arises naturally. If what we see is only part of what exists, what does it mean to talk about the size of the universe at all? And what lies beyond the boundaries set by light and time? Once the idea of a viewing limit settles in, the phrase, the observable universe, begins to carry more weight. It no longer sounds like a technical term used by astronomers for convenience. It becomes a description of a condition, a reminder that everything seen, measured and mapped exists within boundaries shaped not by walls or edges, but by time, motion, and the behaviour of space itself. The observable universe is not the universe in full. It is the portion of the universe from which information has been able to reach this location, here, now. That distinction matters because it separates existence from access. Something can exist without being observable, and in cosmology, that possibility is not just theoretical, it is expected. The observable universe has a radius of about 46 billion light-years. That number is already familiar by now, but it bears repeating carefully, because it behaves differently from almost every distance encountered before. It is not a distance you could ever travel in a straightforward way. It is not even the distance light has travelled through empty space alone. It is a distance defined by how space has stretched while light was moving. When light left the most distant regions we can see, those regions were much closer than they are now. As the light travelled, space expanded. The destination kept moving away. The path itself lengthened. By the time the light arrived, the original source was far beyond where it started. So when we say the observable universe is 46 billion light-years in radius, we are describing the current distance to regions whose light has just had enough time to reach us since the universe became transparent. We are not describing a static sphere. We are describing a dynamic boundary that has grown over time. That boundary is sometimes imagined as a shell surrounding us, but that picture can be misleading. There is no physical surface. There is no glowing edge marking where the universe stops. The boundary is defined entirely by causality, by what can affect what. Inside the observable universe, events can influence one another through signals travelling at or below the speed of light. Outside it, they cannot. Not yet. And in some cases, not ever. This limit feels abstract until it is connected back to the way the universe changes over time. Space is expanding, and that expansion is not slowing down. It is accelerating. The farther away a region is, the faster it recedes due to the expansion of space itself. At sufficiently great distances, this recession becomes so rapid that even light emitted now will never reach us. Those regions are not just currently unobservable, they are permanently beyond reach. This introduces a second, subtler boundary, often called the event horizon. It marks the limit of what will ever be observable, even in the far future. Between the particle horizon, which defines what we can see now, and the event horizon, which defines what we will ever see, lies a region that is temporarily observable. Light from those regions is on its way, but future light will never arrive. These distinctions are not intuitive. They require letting go of the idea that seeing farther simply means waiting longer or building better instruments. Some parts of the universe are not hidden because we lack capability. They are hidden because of how space-time itself behaves. The observable universe, then, is not small, but it is not complete. It is a sample, a very large one, but still a sample. Within that sample, structure appears consistent. Galaxies cluster and form filaments. Voids stretch between them. The cosmic web repeats in every direction surveyed. The cosmic microwave background shows nearly the same temperature everywhere, with only tiny fluctuations. This consistency suggests that the observable universe is representative of the larger whole. There is no obvious reason to believe that conditions suddenly change just beyond the horizon. Physics appears uniform across all observable scales. Still, uniformity does not imply finiteness. The universe could extend far beyond what we can see, continuing with similar structure, similar laws and similar distributions of matter. Or it could be finite but unbounded, wrapping around in a way that does not produce an edge. Or it could be infinite. Current observations cannot distinguish conclusively between these possibilities. Measurements of the universe's geometry suggest that space is very close to flat on large scales. In practical terms, this means that parallel lines do not obviously converge or diverge over cosmic distances. Flatness is consistent with both infinite and extremely large finite universes. If the universe is finite but very large, its full size could be many times larger than the observable portion. If it is infinite, the observable universe is an infinitesimal fraction of the whole. Either way, the observable universe remains a meaningful concept because it defines the limits of interaction. It defines the region where cause and effect can operate relative to this location. This has implications for how size is discussed. When people ask, "How big is the universe?" they are often unknowingly asking two different questions. One is, how big is the observable universe? The other is, how big is everything? The first question has a well-defined answer. The second does not. The observable universe has a measurable size because it is defined by physical processes we understand reasonably well. It grows as time passes, though not indefinitely in a simple way. Its contents can be mapped, counted, and analysed. The total universe, by contrast, may be beyond complete description. This does not mean the question is meaningless. It means the answer depends on assumptions that cannot yet be tested. In everyday experience, boundaries are tangible. A wall stops you, a horizon blocks your view, an edge marks where something ends. The universe does not offer boundaries of that kind. The horizon we encounter is not something you could ever reach physically. No matter how fast you travel, the horizon recedes. It is not located somewhere in space. It is a property of space-time relative to your position and time. If you were to travel to another galaxy, your observable universe would change. Some regions currently visible would fall out of view. Others currently invisible would come into view. Each location has its own observable universe. This reinforces an important idea. There is no single observable universe that belongs to everyone everywhere. There are many overlapping observable universes, one for each point in space. The observable universe discussed here is the one centered on Earth at this moment. It is not privileged. It is simply ours. This realization removes the temptation to treat the observable universe as a container with Earth at the center. Earth is not central in any meaningful cosmic sense. The apparent centrality arises because observation always happens from somewhere. From any galaxy, the observable universe would look similar. A roughly spherical region bounded by a horizon, a cosmic microwave background surrounding everything. Galaxies distributed evenly in all directions on large scales. No matter where you are, you appear to be at the center of what you can see. This symmetry is one of the most striking features of cosmology. It suggests that the universe has no preferred location. There is no central point where everything began expanding outward. Expansion happens everywhere at once. This is often misunderstood as galaxies moving through space away from a central explosion. That image is misleading. Space itself is expanding. Galaxies are carried along with it. Because of this, the observable universe is not expanding into something. It is expanding internally. Distances between distant regions increase, but there is no outside space they expand into. This makes the idea of an edge of the universe difficult to define meaningfully. There is an edge of observation, but not necessarily an edge of existence. When the observable universe is described as having gentle limits, that gentleness is literal. There is no sudden cut-off in what is seen. Galaxies do not stop abruptly. They thin out gradually. Structures blur. light becomes red-shifted beyond detection. At the farthest distances, the universe transitions smoothly from a place filled with discrete objects to a smooth glow. The cosmic microwave background is not a wall. It is a surface of last scattering, a snapshot of a time when the universe changed state. Beyond that surface, the universe did not end. It simply became opaque. The gentleness of these limits stands in contrast to many intuitive ideas about boundaries. There is no cliff, no barrier, no dramatic border, just a gradual loss of information. This gradual fading is why the universe often feels larger than any number assigned to it. Numbers suggest sharpness, boundaries suggest closure. The observable universe offers neither. Even the event horizon, which marks the limit of future observability, is not something you could ever see directly. It does not announce itself. It is defined by trajectories of light and the expansion rate of space. Something could cross the event horizon tomorrow without any visible sign. Its future light signals would simply never arrive. This makes the universe feel subtly incomplete. There are events happening right now that are forever inaccessible from here, not because they are hidden intentionally, but because the geometry of space-time forbids connection. At the same time, there are events within the observable universe whose light has not yet arrived. They exist now, but are unseen. The night sky contains not only images of the past, but absences that represent delayed information. This layered view of existence challenges everyday assumptions about simultaneity. What is happening now across the universe is not something that can be known in any global sense. Now is local. The observable universe is the region whose past intersects with this present. Understanding this does not make the universe feel smaller. It makes it feel deeper. Size becomes entangled with time. Distance becomes entangled with history. The farthest galaxies we observe are not just far away, they are ancient. Their light left when the universe was young, when stars were forming rapidly, when galaxies were smaller and more chaotic. Closer galaxies are seen at later stages. Their structures are more settled, their star formation rates are lower. By comparing these layers, astronomers reconstruct the universe's growth over time. The observable universe is therefore not just a map of space, it is a record of evolution. This record is incomplete, but it is remarkably rich. It tells us about the universe's composition, its expansion history, and its large-scale structure. It reveals the influence of dark matter and dark energy. It shows how complexity emerged from simplicity. Still, the observable universe is only a window. There may be vastly more beyond it, more galaxies, more filaments, more voids, possibly regions with slightly different properties, or perhaps regions identical in every measurable way. Speculation about what lies beyond the observable universe often ventures into ideas like inflation, multiverses, and repeating structures. These ideas are grounded in theoretical physics, but they remain unconfirmed. For now, they remain possibilities rather than conclusions. What can be said with confidence is that the observable universe does not show signs of nearing an edge in structure. Patterns persist up to the limits of observation. Uniformity increases rather than breaks. This suggests that the universe's true size, whatever it is not modest. But rather than trying to imagine that full extent directly, it can be more productive to focus on what the observable universe teaches. It shows that size is not just about length or volume, it is about accessibility, about what can influence what, about the reach of cause and effect. Within this reach, everything encountered so far exists. Earth, the Moon, the Sun, the Solar System, nearby stars, the Milky Way, other galaxies, clusters, filaments, voids. All of it fits within a region defined by the speed of light and the age of the universe. Beyond it, there is silence. Not because nothing is there, but because nothing can speak to us from there. This silence is not emptiness. it is inaccessibility. As this understanding settles, the question of size stops demanding a final number. Instead, it invites a different kind of reflection, one that accepts limits without treating them as failures. The observable universe is vast enough to contain more structure than the human mind can comfortably hold. It is old enough to record nearly the entire history of cosmic evolution. It is large enough that even its smallest details feel significant. If the observable universe has a boundary defined by light and time, then it becomes natural to wonder what exists beyond that boundary. Not dramatically beyond, not in a science fiction sense, just beyond reach. This question does not arise because something appears missing. It arises because everything encountered so far suggests continuity rather than abrupt endings. Galaxies do not stop suddenly. Structure does not collapse at the horizon. Physics does not signal a change. The universe, as far as it can be observed, behaves consistently right up to the limit of what can be seen. So what might lie beyond that limit? The most important thing to say at the outset is also the most restrained. We do not know, not because the question is forbidden, and not because it is meaningless, but because direct evidence is unavailable. Beyond the observable universe, light has not reached us. Information has not arrived. Observation ends not with a wall, but with silence. That silence, however, is not empty of implication. When physicists talk about regions beyond the observable universe, they are not talking about speculative fantasy. They're extending known theories cautiously, asking what those theories predict if they continue to apply beyond what can be measured. The simplest possibility is also the least surprising. The universe beyond the observable horizon may look very much like the universe within it. More galaxies, more clusters, more filaments, more voids. The same large-scale structure repeating, governed by the same physical laws. If this is the case, then the observable universe is just one patch within a much larger expanse. A region defined not by special status, but by circumstance. We see what we see because we are here, now. This idea aligns well with what is called the cosmological principle, the assumption that the universe is homogeneous and isotropic on large scales. That assumption is supported strongly by observations within the observable universe. There is no preferred direction, no obvious center, no region that behaves differently from others. If the universe looks the same everywhere we can see, it is reasonable, though not provable, to suppose it continues to look the same beyond what we cannot see. Under this view, the universe could be vastly larger than the observable region, possibly hundreds of times larger, possibly thousands, possibly infinite. An infinite universe is difficult to imagine, but it is not inherently problematic in physics. Mathematical models allow for infinite space without contradiction. In such a universe, every possible arrangement of matter consistent with physical laws would occur somewhere, given enough space. That idea carries philosophical weight, but it emerges naturally from scale rather than speculation. If space extends without bound, and matter is distributed statistically, repetition becomes inevitable. Still, infinity is not the only option. The universe could be finite but unbounded, meaning it has a total volume but no edge. This is similar to the surface of a sphere. You can travel in one direction indefinitely without encountering a boundary, yet the total area is finite. In 3 dimensions, this is harder to visualize, but the mathematics is well understood. Space could curve back on itself. If it does, the universe could be finite while still having no edge. In such a universe, traveling far enough in a straight line could, in principle, bring you back to your starting point. Not because space loops like a tunnel, but because its geometry is closed. Observations so far suggest that the universe is very close to flat. That does not rule out slight curvature on scales much larger than the observable universe. If curvature exists, it is subtle enough that it does not show up within current measurement limits. This leaves open the possibility that the universe is finite but far larger than what we can observe. There is also the idea that beyond the observable universe lie regions shaped by processes that occurred very early on, during a phase called cosmic inflation. Inflation is a theory that proposes a brief period of extremely rapid expansion in the early universe. According to inflationary models, space expanded exponentially in a fraction of a second, smoothing out irregularities and setting the stage for the universe we observe today. If inflation occurred, it may not have ended everywhere at once. In some versions of the theory, inflation continues in some regions while stopping in others. This leads to the concept of a multiverse, where our observable universe is one region among many, each with potentially different properties. It is important to be careful here. The word multiverse is often used loosely, and it can carry connotations that go far beyond what the physics actually suggests. In this context, it does not necessarily mean wildly different laws of nature or exotic realities. It could mean regions of space that are simply disconnected from one another by inflationary expansion. These regions would not be reachable, not now, not ever. They would exist beyond causal contact. From within one region, there would be no way to observe another directly. The horizon would remain absolute. This idea is controversial, not because it is mathematically unsound, but because it is difficult to test. Science relies on observation, and regions beyond the observable universe cannot be observed directly. Some physicists argue that inflation makes testable predictions about the observable universe that can be checked, lending indirect support to the broader framework. Others remain cautious, emphasizing the importance of falsifiability. Regardless of where one stands on inflation or multiverse ideas, the key point for understanding size remains the same. The universe may be much larger than what we can see, possibly unimaginably larger. What lies beyond the observable edge does not have to be exotic to be profound. Even if it is simply more of the same, the scale implied is enormous. Consider this quietly for a moment. If the observable universe contains hundreds of billions of galaxies, and if it represents only a fraction of the whole, then the total number of galaxies could exceed anything that can be counted meaningfully. The mind naturally resists this. It tries to anchor size to something familiar. It searches for a largest thing, a final boundary, a conclusion. The universe offers none. Instead, it offers horizons, limits of access rather than limits of existence. This distinction is subtle but important. When people ask what lies beyond the edge of the universe, they often imagine an edge like the boundary of land meeting ocean, a place you could reach, cross, or peer over. The universe does not seem to work that way. There is no indication of a physical edge where space ends and something else begins. Space does not appear to be embedded in a larger container. Beyond the observable horizon, space likely continues, or curves, or transitions in ways that cannot yet be described with certainty. Another possibility is that the universe is finite, and the observable horizon is close to its true extent. This would require specific conditions in the universe's geometry that have not yet been detected, but it cannot be ruled out entirely. If that were the case, then beyond the observable universe might not lie much more at all. The horizon would represent not just a limit of observation, but a limit of space itself. Current evidence does not favour this strongly, but cosmology is a field where humility is necessary. The universe has a habit of being larger and more complex than expected. One of the most striking features of the observable universe is how uniform it is. The cosmic microwave background looks nearly the same in all directions. Temperature variations are tiny. This uniformity extends across regions that, under simple expansion models, should not have been able to exchange information. This observation was one of the motivations for inflation theory. It suggests that regions now far apart were once close together. If inflation occurred, it may have smoothed out the universe on scales far larger than what we can see. In that case, what lies beyond the horizon would be more of the same uniform structure. But even uniformity can be misleading. On smaller scales, the universe is anything but uniform. It is full of structure, contrast, and complexity, filaments and voids, clusters and isolated galaxies, order emerging from slight imbalance. This raises the possibility that beyond the observable universe, structure continues to form and evolve, shaped by the same processes, but at times and places we will never observe. These regions would not be frozen. They would not be static. Stars would form and die, galaxies would merge, clusters would grow, all without ever influencing this location. That idea can feel strange, events happening forever beyond awareness. But this is already true on smaller scales. There are stars in our own galaxy whose light will never reach Earth because it is absorbed or scattered. There are neutrinos passing through your body right now from distant sources you will never know. The universe does not require observation to exist. Another way to think about what lies beyond the edge is to reverse perspective. Imagine an observer in a distant galaxy, far beyond our observable horizon. That observer would have their own observable universe, centered on their location. Their horizon would include regions invisible from here. It would exclude regions visible here. From their perspective, Earth might lie beyond their horizon, permanently unreachable. This symmetry reinforces the idea that horizons are local, not universal. Each observer sees a different slice of the universe. There is no global vantage point from which the entire universe can be seen at once. This absence of a privileged perspective is one of the most consistent themes in modern cosmology. There is no centre, no edge that belongs to everyone, only overlapping horizons defined by location and time. When this idea is allowed to settle, the question of what lies beyond the edge changes tone. It becomes less about finding a final answer and more about understanding the nature of limits. The edge is not a place, it is a condition. It is the point beyond which cause and effect no longer connect to this moment. It is not marked by matter or light, it is marked by silence. That silence is not ominous, it is simply neutral. Speculating responsibly about what lies beyond the observable universe requires accepting uncertainty. It requires distinguishing between what is known, what is inferred, and what is unknown. What is known is that the universe within the observable horizon follows consistent physical laws. What is inferred is that those laws likely apply elsewhere. What is unknown is how far that elsewhere extends. Some theories suggest that the universe may be far larger than the observable region, by factors so large they defy intuition. Others suggest more modest extensions. None of these possibilities change the fact that the observable universe already contains more space, matter, and history than any single mind can absorb fully. In that sense, what lies beyond the edge is not necessary for the universe to feel vast. It is already vast. But curiosity does not stop at sufficiency, it continues. As understanding deepens, the question of size gradually stops being about measurement alone. It becomes about perspective, about recognizing that existence may extend far beyond awareness, and that this does not diminish what is known. Instead, it places it in context. The universe does not reveal itself all at once. It reveals itself partially, through light that arrives slowly, through patterns that emerge gradually, through theories that extend beyond observation cautiously. Beyond the observable horizon, there may be more of the same, or something subtly different, or structures that echo what is seen here with slight variations. We do not know. And that not knowing is not a failure. It is a boundary condition of being inside the universe rather than outside it. After travelling mentally from Earth to the edge of everything that can be seen, the most grounding question becomes a quiet one. How does this vastness relate to where you are now? Here, listening, anchored to a small world that exists fully inside it all. After stretching outward through distances that resist intuition, there is a natural tendency to pause, not because the universe has ended, and not because curiosity is exhausted, but because attention wants to return to something solid, something familiar. After considering stars counted in the billions and spaces measured in billions of light years, it becomes meaningful again to notice where all of this thinking began. It began here. Right now, wherever you are, you're resting on a small planet orbiting an ordinary star inside one galaxy, among countless others. That description can sound diminishing at first. Small planet, ordinary star, one among many. But smallness in this context is not the same as insignificance. It is simply scale. Earth has always been small in the cosmic sense. It did not become smaller when galaxies were discovered or when the observable universe was measured. What changed was context. The frame widened, the background expanded. What did not change was what Earth is. This planet still has oceans that move with the pull of the moon. It still has an atmosphere thin enough to protect life and thick enough to shape weather. It still supports chemistry complex enough to produce thought, memory and curiosity. None of that is undone by the size of the universe. Perspective does not erase meaning. It reframes it. It can be tempting, after a long mental journey outward, to feel a kind of vertigo, to wonder how anything so small could matter in a universe so large. That reaction is understandable, but it rests on a quiet assumption that size determines value. Physics does not support that assumption. In physical terms, small systems often have enormous importance. A single gene can alter the development of an organism. A minor chemical imbalance can change the behavior of an entire ecosystem. A tiny fluctuation in the early universe became the seed of galaxies. Scale does not dictate influence. Context does. Earth occupies a tiny fraction of the universe's volume, but volume is not the only metric that matters. This planet is a place where matter has organized itself into layers of complexity rarely seen elsewhere, at least as far as current evidence shows. From the perspective of physics, Earth is not remarkable because it is large or massive. It is remarkable because it is structured in a particular way. It maintains stable conditions over long periods. It cycles energy efficiently. It supports systems that can observe and reflect on the universe itself. That last point deserves attention. Everything discussed so far, every distance measured, every structure described, is known because observation is happening somewhere. Telescopes are built on planets. Instruments are designed by minds. Data is interpreted by conscious systems embedded within the universe they study. The universe does not describe itself. It is described from within. This means that returning attention to Earth is not a retreat from cosmic scale. It is an acknowledgement of where understanding actually occurs. From this planet, humans have learned to measure the distance to the moon using laser pulses. They have learned to infer the presence of dark matter by observing how galaxies move. They have mapped the cosmic microwave background and extracted information about the universe's earliest moments. All of that knowledge emerged from a thin layer of life on a small world. That fact does not contradict the vastness of the universe. It complements it. When the universe is viewed purely as size and distance, it can feel impersonal. But when it is viewed as a system that has produced at least one place capable of asking questions about it, something shifts. The universe becomes not smaller, but more interesting. Earth is not central. It does not occupy a privileged location. It is not unique by necessity, but it is specific. It is a particular outcome of physical processes playing out under particular conditions. Those processes appear to operate everywhere. Stars form in many galaxies. Planets form around many stars. Chemistry is universal. The same elements found here are found across the cosmos. This raises a quiet possibility. Earth may not be the only place where complexity has emerged. Other planets may host life. Other regions may harbour systems capable of observation. Distance currently separates these possibilities from confirmation. but distance does not negate their plausibility. In this sense, Earth is not alone in principle, it is alone in experience for now. Coming back home after contemplating the universe's size does not mean shrinking attention. It means anchoring it, letting the scale settle without letting it overwhelm. When you think about Earth now, it might feel different than it did before. Not smaller, exactly, but more defined. More clearly placed within a vast structure that extends far beyond immediate awareness. That placement does not diminish Earth's reality, it situates it. Consider again where you are physically: a room, a bed, a chair, the ground beneath you, the air around you. All of this exists within Earth's atmosphere, which exists within Earth's gravitational field, which exists within the Sun's orbit, which exists within the Milky Way, which exists within a filament of the cosmic web, which exists within the observable universe. This nesting is not abstract, it is literal. Everything local is embedded within something larger, and that larger thing is embedded within something larger still. At no point does the chain break. There is continuity all the way out, and yet from the inside each layer feels complete. Earth feels like a whole world because it is one. The solar system feels like a complete system because it functions as one. The Milky Way feels immense because it is immense. Perspective does not invalidate local completeness. This matters because it allows both views to coexist. Earth can be small and still be sufficient. The universe can be vast and still be coherent. When people imagine the edge of the universe, they often picture a boundary beyond which there is nothing. But what has emerged instead is a different kind of boundary, one defined by observation, not by existence. This means that coming back home is not a retreat from truth, it is a return to the only place from which truth is ever accessed. The night sky, when seen from Earth, is no longer just a ceiling dotted with lights. It becomes a cross-section through layers of time and space. Each star is a local neighbour. Each faint galaxy is a distant system seen as it once was. Each patch of darkness may hide structures too faint or too far to detect. Yet the sky still looks calm. That calmness is not deceptive. It reflects the slow pace at which cosmic change unfolds on human timescales. Stars do not flicker in and out of existence. Galaxies do not rush past. Expansion is imperceptible moment to moment. The universe is dynamic, but it is not hurried. This slowness is part of what makes understanding possible. If the universe changed rapidly on human timescales, patterns would be harder to detect. Stability allows accumulation of knowledge. Earth benefits from that stability. Orbits are predictable. Physical laws are consistent. Conditions persist long enough for complex systems to develop. That persistence is not guaranteed everywhere. It arises from a balance of forces and parameters that need not be universal. Again, this does not make Earth special in a cosmic sense. It makes it fortunate. Returning home in thought also invites reflection on scale in a different direction. So far, size has been considered mostly outward, from Earth to the Moon, from the Sun to the stars, from galaxies to the observable universe. But scale also extends inward. The same physical laws that govern the expansion of space govern the interactions of particles. Atoms are mostly empty space. Nuclei are tiny compared to the size of atoms. Subatomic particles occupy scales far removed from everyday experience. In that sense, Earth sits not only between the very large and the very far, but also between the very small and the very near. It is a midpoint where multiple scales intersect. This intersection is not arbitrary. It is where complexity thrives. Life requires energy gradients, stable environments, and time. Those conditions exist most readily at intermediate scales. Too small, and systems fluctuate too violently. Too large, and structure thins out. Earth occupies a narrow band where chemistry can organize itself into biology, where biology can develop nervous systems, and where nervous systems can ask questions about the universe. That alone is enough to resist the idea that small equals insignificant. The phrase small but not insignificant is not a comfort phrase. It is a factual description. Earth's mass does not affect the motion of galaxies. Its gravity does not shape the cosmic web. But significance is not measured by gravitational influence alone. Significance can also be measured by what exists, what happens, and what is possible. On Earth, there is memory, there is language, there is accumulated understanding, there is curiosity that reaches outward far beyond local conditions. That curiosity has allowed a species on this planet to infer the age of the universe, the structure of galaxies, and the limits of observation without ever leaving its home system. That achievement does not require exaggeration. It stands on its own. Coming back home does not mean concluding the journey. It means recognizing that the journey was never about leaving in the first place. It was about widening perspective while remaining grounded. Even now, the universe continues to expand. Light continues to travel. Structures continue to evolve. Regions move beyond horizons. New regions become observable. All of that is happening regardless of whether it is noticed. And yet, here, on Earth, awareness continues. There is something quietly remarkable about that alignment. A universe capable of being measured. A location capable of measuring it. This alignment does not require purpose or intention to be meaningful. It simply is. As attention settles again into the local, the room, the breath, the steady presence of being here, the universe does not shrink back into the sky. It remains vast. It remains layered. It remains largely unknown beyond certain limits. What changes is not the universe, but the relationship to it. Instead of feeling dwarfed by scale, it becomes possible to feel placed within it. Instead of seeing smallness as negation, it becomes context. Earth is not the center of the universe, but it is a center of experience, a point from which observation occurs. One of many possible points perhaps, but no less real for that. And from this point, everything discussed remains true. The moon still orbits, the sun still shines, the Milky Way still rotates, galaxies still cluster, the cosmic web still stretches across the observable universe. Beyond it, space likely continues. None of that requires resolution tonight. Understanding the true size of the universe is not about reaching an endpoint. It is about becoming comfortable with expansion, with the idea that scale does not have to terminate neatly to be meaningful. The universe does not ask to be grasped all at once. It reveals itself in layers, and it allows those layers to coexist, here and there, small and vast, near and far, known and unknown. Coming back home, then, is not about closing the subject. It is about letting the scale rest where it naturally settles without strain. Earth remains a small world in a very large universe. That has always been true. What has changed over time is awareness of that fact. And awareness, once expanded, does not need to stay stretched. It can relax, carrying perspective without effort. The universe continues whether it is being thought about or not. Stars burn. Galaxies drift. Light travels. Here, on this planet, in this moment, it is enough to simply be aware that all of this exists, that it extends far beyond immediate experience, and that despite its vastness, it includes places where understanding can arise. That understanding does not conquer the universe, it accompanies it. And from here, quietly grounded on a small world, orbiting an ordinary star, the universe does not feel less meaningful for being large. It feels more complete for being able to be known at all, even partially, even imperfectly, from a place that remains, in every practical sense, home.